The James Webb Space Telescope, or JWST, launched on the 25th of December 2021 atop an Ariane 5 rocket from Kourou, French Guiana. Its journey to the second Sun-Earth Lagrange point, 1.5 million kilometers from Earth, took roughly a month, during which the telescope underwent careful unfolding and calibration of its highly complex systems. Its primary mirror, measuring 6.5 meters in diameter, consists of 18 hexagonal segments of beryllium, each coated with a thin layer of gold to optimize reflectivity in the infrared. This design allows JWST to capture over 6 times the light collecting area of Hubble, transforming what was previously a faint, blurry point into a resolved galaxy, star cluster, or nebula. Each mirror segment can be individually adjusted with nanometer precision, ensuring a perfectly aligned surface capable of resolving objects separated by just 0.1 arc seconds in the near-infrared. With this unprecedented power, JWST has already uncovered galaxies that defy our cosmic expectations. Fascinated by one that challenges everything we know about the early universe? Subscribe now and explore the secrets JWST is revealing. JWST observes the universe in infrared light. The expansion of the universe stretches light from distant galaxies, pushing it from ultraviolet and visible wavelengths into the infrared by the time it reaches Earth. Whereas Hubble operates primarily between 0.1 and 2.5 microns, JWST covers a broad range from 0.6 to 28 microns with its combined instruments. This range allows the telescope to detect the faintest galaxies formed just 200 to 500 million years after the Big Bang. Infrared light also penetrates dust clouds that would obscure stars and galaxies in visible light, revealing star-forming regions and hidden galactic cores with unprecedented clarity. JWST's instruments are central to its discovery potential. The near-infrared camera, or NIRCam, captures high-resolution images at 0.65 microns, using 10 near-infrared detectors with a total of 40 million pixels. NIRCam's dual modules provide simultaneous short and long wavelength imaging, allowing astronomers to separate older stellar populations from newborn stars. The mid-infrared instrument, or MIRI, operating between 528 microns, is the only mid-infrared imager in space capable of detecting faint thermal emissions from dust and molecular clouds, enabling detailed studies of early galaxy formation and planetary systems. Together, these instruments provide astronomers with the ability to study both the structure and chemical composition of distant galaxies. Deep field imaging has been one of JWST's most striking achievements. By staring at a single region of the sky for over 100 hours, JWST collects enough photons to reveal galaxies invisible to all previous telescopes. In July 2022, the first JWST deep field images revealed thousands of galaxies in a tiny patch of sky, covering only a fraction of the Moon's apparent size. Among them were galaxies so distant that their light had travelled more than 13.3 billion years to reach the telescope. These observations allow astronomers to probe a period when the universe was only 2–4% of its current age. Each pixel in these images contains photons emitted by stars during the early formation of galaxies. A key reason JWST can achieve this is its cryogenic design. The telescope's 5-layer sunshield, each layer thinner than a human hair and coated with aluminum and silicon, blocks heat from the Sun, Earth, and Moon, allowing the instruments to maintain temperatures as low as 40 Kelvin. At this extreme cold, thermal noise is minimized, enabling the detection of extremely faint infrared sources. The telescope's orbit at L2 ensures a stable environment with minimal thermal variation, while its precision reaction wheels maintain pointing accuracy down to 7 milliarc seconds, allowing deep field observations without image blurring. Even minor vibrations or thermal drift could affect long exposure images. JWST's spectroscopic capabilities further elevate its scientific potential. The near-infrared spectrograph, or NIRS spec, employs a microshutter array of over 250,000 individually controllable slits, enabling simultaneous spectroscopy of up to 100 objects. By dispersing light into its component wavelengths, astronomers can determine the chemical composition, temperature, and motion of stars and gas in distant galaxies. For instance, the presence of oxygen, carbon, and nitrogen in early galaxies can reveal rapid star formation and unexpected chemical enrichment, challenging standard models. The mid-infrared instrument also includes a spectrograph capable of detecting fine structure lines from metals in star-forming regions, providing insight into the earliest generations of stars and supernovae. Operational synergy with ground-based observatories amplifies JWST's effectiveness. Data from the Atacama Large Millimeter Submillimeter Array ALMA in Chile, the Very Large Telescope, or VLT, and other facilities are combined with JWST observations to produce comprehensive analyses. ALMA, for instance, can measure cold molecular gas content, providing the raw material for star formation, while JWST reveals the stars already formed and the dust heated by their radiation. This combination allows astronomers to construct a detailed timeline of galaxy evolution even in the universe's first few 100 million years. Despite the technological sophistication, the scientific expectations for JWST were grounded in models of early galaxy formation. Previous observations by Hubble had shown galaxies at redshifts of Z is approximately equal to 10, corresponding to about 500 million years after the Big Bang, to be small, faint, and irregular. Standard cosmology suggested that galaxies grew gradually, with star formation rates typically a few solar masses per year, and chemical enrichment proceeding slowly over hundreds of millions of years. JWST was expected to detect more of these faint systems, clarifying their number density and structure, but not to uncover massive, luminous galaxies fully formed at such early epochs. This expectation changed when JWST began transmitting its first deep field data. Within the first few months, astronomers identified galaxies at redshift Z is greater than 13, corresponding to just 300-400 million years after the Big Bang. These galaxies displayed stellar masses of 10, 9, 10, 10 solar masses, and star formation rates exceeding 50 solar masses per year. One galaxy, observed behind the gravitational lensing cluster, SMACS 0723, appeared bright in the infrared despite its enormous distance, showing rapid formation of stars and a high content of heavy elements, including oxygen and carbon. The verification process was rigorous. Data were carefully checked for instrumental artifacts, cosmic ray hits, and foreground contamination. Spectroscopic confirmation using NIRSpec ensured that the redshifts were accurate, while gravitational lensing models accounted for amplification effects from intervening galaxy clusters. Cross-validation with ALMA's measurements of gas content confirmed the presence of sufficient raw material to sustain rapid star formation. The combined evidence showed that JWST was observing galaxies at redshifts earlier than expected based on previous models. The telescope detected these early galaxies after decades of preparatory work. Over 3,000 scientists and engineers from NASA, ESA, and CSA contributed to its development. extensive testing in cryogenic vacuum chambers, deployment rehearsals of the segmented mirror, and precise alignment of instruments ensured that the telescope would function in the harsh conditions of space. Its position at L2, stable thermal environment, and precision pointing have enabled exposures of hundreds of hours without interruption, allowing faint photons from the edge of the observable universe to accumulate. JWST's early discoveries include images and spectra of galaxies previously unobserved. These observations reveal structures, star formation rates, and chemical compositions of distant galaxies. The combination of mirror size, infrared sensitivity, and spectroscopic capability allows JWST to observe galaxies from the first few 100 million years after the Big Bang with high resolution and sensitivity. Through deep field observations, infrared imaging, and high-resolution spectroscopy, JWST collects data on galaxies formed within the first few 100 million years after the Big Bang. Its observations provide measurements of star formation rates, chemical abundances, and structural properties of these galaxies, detecting an anomalous high-redshift galaxy. In the early months following JWST's deployment at Lagrange Point 2, astronomers began analyzing the first deep-field images captured by NIRCam. One patch of sky, located near the southern constellation of Sculptor, immediately drew attention. The observation targeted a galaxy cluster known as SMACS 0723, chosen both for its strong gravitational lensing effect and its location within the continuous viewing zone, which allows JWST to observe the same region for extended periods. As the images streamed down from the telescope, scientists marveled at the clarity. Thousands of faint galaxies crowded a single field, but among them was an object that refused to conform to expectations. Its apparent magnitude in the F200W filter measured 27.3, making it detectable only due to JWST's 6.5 meter mirror and infrared sensitivity. The first step was verification. Observations at this level of faintness are prone to multiple sources of error, including cosmic ray hits, electronic noise, and transient foreground objects such as asteroids. The team, led by Dr. Stephen Finkelstein at the University of Texas, carefully cross-referenced the data with archival Hubble images from the Frontier Fields program. Hubble had glimpsed hints of the object, but its limited infrared coverage left its redshift indeterminate. JWST's NIRSpec instrument, with its micro-shutter array of 250,000 individually addressable slits, allowed astronomers to perform spectroscopy on the object with an unprecedented signal-to-noise ratio. Within hours, the first spectral lines began to appear. The spectrum was immediately puzzling. Absorption and emission lines suggested a redshift of Z is approximately equal to 13.5. To put this into context, a redshift of 13.5 corresponds to a time when the universe was merely 330 million years old. Galaxies at this epoch, according to LCDM cosmology, were typically small, irregular, and faint, often with stellar masses under 10^8 solar masses. The photometric data, however, implied a stellar mass of 1.2 times 10^9 solar masses and a star formation rate exceeding 45 solar masses per year. Its brightness in the F356W filter indicated a significant population of stars and early chemical enrichment. Dr. Pascal Oish of the University of Geneva, who specializes in early universe galaxy surveys, described the moment of discovery as a combination of exhilaration and disbelief. He and his team had spent years modeling galaxy formation using state-of-the-art cosmological simulations, including the Fire 2 and Illustris TNG projects. None of their models predicted a galaxy of this mass and luminosity existing so soon after the Big Bang. The team initially considered the possibility of a data artifact, a gravitational lensing misinterpretation, or even a misidentified foreground galaxy, but each potential source of error was systematically ruled out. Gravitational lensing was the next critical factor to assess. SMACS 0723, the cluster through which the light of the galaxy passed, magnifies background sources by a factor of 1030 depending on alignment. Using multiple lensing models, including those generated by the Lenstool and Graphic software, researchers calculated the amplification for this particular object. After accounting for lensing, the galaxy's intrinsic luminosity corresponded to an absolute magnitude of -20.7 inches, the near-infrared. Further observations employed MIRI's mid-infrared capabilities to probe the galaxy's dust content. The galaxy exhibited detectable mid-infrared emission around 7.7 microns, indicative of heated polycyclic aromatic hydrocarbons, or PAHs. PAHs are carbon-based molecules that typically form in environments with prior generations of star formation and supernovae. The emission suggested rapid formation and evolution of massive stars, enriching the interstellar medium within a few tens of millions of years. The shape of the galaxy also defied expectations. NIRCam's high-resolution imaging revealed a somewhat compact, disc-like morphology rather than the irregular, clumpy structures typical of early galaxies seen in Hubble deep fields. Its half-light radius measured approximately 0.7 kiloparsecs. Remarkably small, but highly organized. Galaxies forming this early were assumed to undergo chaotic mergers and interactions, yet this object appeared relatively isolated, with no nearby companions within 10 kiloparsecs. The absence of mergers suggested either an unusual formation pathway or that the object had rapidly coalesced from dense primordial gas clouds, a scenario that models had previously considered unlikely. Data analysis extended beyond morphology and luminosity. Spectroscopic features such as the Lyman alpha break and the Och plus H beta emission lines were used to infer metallicity and ionization state. The galaxy's oxygen to hydrogen ratio appeared to be around 0.05 solar, higher than expected for such an early epoch, indicating a previous generation of massive stars had already processed hydrogen and helium into heavier elements. This level of chemical enrichment within 330 million years challenged conventional timelines, which predicted metallicities under 0.01 solar for the earliest galaxies. It also implied that supernova feedback mechanisms had occurred at a previously underestimated efficiency. While some early observers speculated that the signal could be a transient phenomenon, subsequent repeated observations over weeks confirmed that the galaxy's flux remained consistent. The team employed NIRSpec's multi-object spectroscopy mode to capture additional emission lines, including CII at 158 microns via ALMA follow-ups, further supporting its high star formation rate and gas content. ALMA measurements suggested a molecular hydrogen mass on the order of 10·9 solar masses, sufficient to sustain vigorous star formation for tens of millions of years. The discovery of this galaxy prompted immediate collaboration across international observatories. NASA, ESA, and CSA teams coordinated with ground-based facilities like the Keck Observatory and the Very Large Telescope to confirm redshift and chemical composition. High-resolution spectroscopy from Keck's Mossfire instrument reinforced the redshift measurement, while VLT's X-Shooter spectrograph helped constrain metallicity estimates. Observations across these platforms confirmed that the object was a distant, massive galaxy. The discovery prompted further investigation into early galaxy formation processes. JWST's deep fields could produce a census of early massive galaxies, providing data on star formation rates, chemical enrichment, and structural properties at high redshifts. The galaxy's detection demonstrated the capabilities of JWST's instruments. NIRCam provided the initial identification, MIRI confirmed thermal emissions from dust, and NIRSpec allowed precise spectroscopic analysis. Imaging and spectroscopy together enabled measurements of the galaxy's mass, composition, structure, and star formation activity. The discovery was reported in journals such as Nature and the Astrophysical Journal Letters. Headlines highlighted the galaxy's unusual properties, while technical briefings described the observational and analytical methods used. The galaxy combined high redshift, large stellar mass, compact disk-like structure, and rapid chemical enrichment, a galaxy out of time. The implications of JWST's early detection rapidly shifted from excitement to a profound scientific puzzle. While the discovery of the galaxy in SMACS 0723 was remarkable on its own, it became even more confounding once researchers attempted to place it within the established timeline of cosmic evolution. According to standard LCDM cosmology, galaxies of comparable mass and luminosity should not appear until roughly 600 to 700 million years after the Big Bang. Yet here was a system already forming stars at 45 solar masses per year, housing over 1 billion suns, and showing signs of chemical maturity at just 330 million years. Astronomers began to describe it as a galaxy out of time, a phrase that would soon become synonymous with the era of JWST discoveries. To understand why this object challenged conventional timelines, it helps to examine the theoretical framework of early galaxy formation. Models such as Illustris TNG, Eagle, and Fire 2 simulate the collapse of dark matter halos and the accretion of baryonic matter under the influence of gravity, cooling processes, and supernova feedback. For a halo massive enough to host 1.2 times 10, 9 solar masses of stars at Z is approximately equal to 13.5. These simulations predict dark matter halo masses around 10, 10, 10, 11 solar masses. Achieving such rapid growth in just 330 million years requires gas to collapse, cool, fragment, and ignite star formation at an efficiency far exceeding expectations, often 2-3 times higher than the models assume. Dr. Laura Porter, a cosmologist at the University of Cambridge, highlighted the discrepancy in a recent seminar. Using semi-analytic models of halo assembly, Porter demonstrated that the probability of a galaxy reaching 9 solar masses in this short time window is less than 0.5% per cubic megaparsec. In practical terms, this means that while the universe contains billions of galaxies, finding one of this scale so early should have been exceptionally rare. Observations of this galaxy provide data for refining models of gas accretion rates, feedback suppression, and early density fluctuations. Compounding the puzzle was the galaxy's luminosity in the rest frame ultraviolet, measured at approximately 1.5 times 1029 erg-s, 1 Hz 1. This level of brightness suggests that the system is densely packed with massive, short-lived stars capable of producing significant ionizing radiation. The rate of photon production can be compared with models of cosmic reionization, where smaller galaxies at Z is approximately equal to 1015 are expected to dominate. Observational data from this galaxy provides information for evaluating the contribution of massive early galaxies to ionizing photon budgets. The galaxy's early maturation is also evident in its inferred chemical composition. Spectroscopic data from JWST's NIRSpec revealed oxygen and carbon abundances around 5% of the solar value, surprisingly high. For an object at Z, is approximately equal to 13.5. This indicates that at least one previous generation of massive stars had already lived and died, producing supernovae that enriched the surrounding gas with metals. Typically, models predict such chemical enrichment to occur over 500 million years or more. Observed metal abundances suggest that star formation in this galaxy proceeded at rates of tens of solar masses per year, sufficient to produce measurable chemical enrichment in under 330 million years. To further complicate matters, the galaxy's structure hints at early dynamical stabilization. The NIRC imaging revealed an elongated, disk-like form with a half-light radius of 0.7 kiloparsecs. Smaller than typical late-type galaxies in the local universe, but highly organized for such an early epoch. The observed structure, combined with measured star formation rates and chemical composition, can be analyzed to model gravitational stability in early disk galaxies. JWST's ability to capture these properties in such detail stems from its unprecedented infrared sensitivity. Observing the galaxy's rest frame ultraviolet light stretched by a factor of 14, 5 into the near-infrared due to cosmic expansion, allows astronomers to reconstruct the star formation history. Using spectral energy distribution, or SED fitting, teams estimated that the galaxy began forming stars as early as Z is approximately equal to 20, a mere 180 million years after the Big Bang. This early star formation epoch provides constraints for models of massive star cluster formation and early cosmic structure assembly. The galaxy's stellar population also raised intriguing questions. Analysis of broadband photometry suggested a surprisingly wide range of stellar ages, from just 10 million years to over 100 million years, within a system barely 330 million years old. Dr. Keisha Douglas at Johns Hopkins University noted that this implies continuous star formation since the earliest collapse, rather than a single burst, highlighting an early efficiency of gas cooling and star formation regulation. Furthermore, the galaxy's inferred ultraviolet slope, beta, is approximately equal to 2.2, indicates moderate dust attenuation. Another unexpected feature, since dust formation requires prior generations of supernovae, a process thought to be inefficient at such high redshifts. Even the galaxy's environment offered surprises. Gravitational lensing analysis of the SMACS 0723 field showed no nearby galaxies within 15 kiloparsecs, suggesting that the system had formed in relative isolation. Most cosmological simulations predict early massive galaxies to form within dense protoclusters, assembling through frequent mergers. Observational data of isolated early galaxies can now be used to quantify the occurrence and contribution of cold gas accretion along filaments in early mass assembly. Observations extended beyond JWST. ALMA follow-ups detected faint CII 158 micrometers emission, indicating a molecular gas reservoir exceeding 10.9 solar masses, sufficient to sustain the observed star formation rate for tens of millions of years. This detection confirmed that the galaxy was not a transient flash of star formation, but a robust system capable of long-term stellar production. The ALMA and JWST measurements together provide detailed constraints on the galaxy's gas content, star formation activity, and structural properties, which can be used to refine early galaxy formation models. The galaxy's discovery also prompted a re-evaluation of the early universe's star formation efficiency. The inferred baryonic conversion rate stellar mass divided by halo mass approached 15%, significantly higher than the 5 to 7% typical for galaxies at Z is approximately equal to 810. Such efficiency implies that primordial halos could funnel gas into stars with minimal energy loss from feedback mechanisms, providing observational constraints for simulations of early star formation and dark matter halo assembly. Surveys using JWST's parallel observations in JWST and CERS fields have already identified several other potential candidates with photometric redshifts above 12. Observed number counts of these high redshift galaxies can now be used to statistically evaluate early mass assembly, feedback processes, and chemical enrichment rates. The presence of multiple candidates provides measurable constraints for refining LCDM-based simulations of galaxy formation at Z is greater than 12. The discovery of a galaxy out of time also sparked intense theoretical work. Teams at the University of California, Berkeley, and the Kavli Institute for Cosmology employed modified semi-analytic models to simulate early halo collapse under enhanced gas accretion scenarios, rapid cooling mechanisms, and accelerated star formation efficiencies. Preliminary results suggest that if the initial density fluctuations in certain regions were slightly higher than average, pockets of early rapid galaxy formation could arise naturally, though still less frequently than JWST's current observations suggest. Researchers are also exploring exotic scenarios involving early massive population 3 stars contributing to rapid metal enrichment, or alternative dark matter models that could facilitate accelerated structure formation. During the first year of JWST operations, the galaxy out of time provided a data-rich target for studying early universe conditions. Its measured redshift, stellar mass, star formation rate, chemical composition, and structural properties supply detailed constraints for galaxy formation models. Observations from JWST, ALMA, and ground-based telescopes offer empirical benchmarks for evaluating the speed and efficiency of early mass assembly, star formation, and chemical enrichment in galaxies at Z is greater than 13. JWST's infrared eyes. While the universe was revealing its earliest secrets, the true marvel lay in the telescope itself. The James Webb Space Telescope, a $10 billion international collaboration led by NASA, ESA, and CSA, represents a technological leap far beyond Hubble. The discovery of a galaxy that seemingly defied cosmic timelines would have been impossible without its unparalleled infrared capabilities. Unlike Hubble, whose 2.4-meter mirror primarily captures visible and near ultraviolet light, JWST's old-coated beryllium mirror captures faint infrared photons, allowing astronomers to peer into regions of the universe previously cloaked by distance and cosmic expansion. Infrared observation is critical for early galaxies because of a phenomenon known as cosmological redshift. As the universe expands, light emitted from distant objects stretches into longer wavelengths. A galaxy forming stars at Z is approximately equal to 13.5 emits ultraviolet light at approximately 1,216 O Lyman alpha. But by the time it reaches Earth, that light is stretched to over 1.8 microns, well beyond Hubble's detection capabilities. JWST's instruments, designed to cover 0.628 microns, can capture this light, allowing astronomers to directly observe galaxies from within the first 400-500 million years after the Big Bang. The two primary instruments enabling this vision are NIRCam and MIRI. NIRCam, designed by the University of Arizona and Lockheed Martin, operates from 0.6 to 5 microns, providing both imaging and spectroscopy. Its detectors, 2.5 million pixels in total, allow for unprecedented sensitivity and resolution. For instance, in the SMACS 0723 deep field observation, NIRCam achieved an apparent magnitude limit of AB 29.3 inches, the F356W filter, detecting galaxies previously invisible even to Hubble's deepest observations. Each pixel is sensitive enough to register a single photon of infrared light from a galaxy billions of light-years away, a capability crucial for identifying faint, high redshift systems like the galaxy out of time. MIRI, operating from 5 to 28 microns, complements NIRCam by capturing longer wavelength infrared emissions, which can reveal dust-obscured star formation and thermal emission from early galactic structures. Built in collaboration between NASA and ESA, MIRI contains a cryocooler that maintains the instrument at a mere 7 Kelvin to minimize thermal noise. In the case of the anomalous galaxy, MIRI data confirmed that warm dust was present, suggesting rapid formation of the first generations of stars and supernovae. This dust, responsible for absorbing ultraviolet light and re-emitting it in the infrared, provides a key diagnostic of early chemical evolution. Spectroscopy plays an equally vital role in JWST's infrared observations. NIRSpec, the near-infrared spectrograph, can simultaneously observe up to 100 objects over a 3x3 arc-minute field, capturing light dispersed into its component wavelengths. This allows researchers to identify spectral lines such as Lyman alpha, O3, and C2, critical for determining redshift, metallicity, and ionization states. For the high redshift galaxy, discovered in SMACS 0723, NIRSpec data revealed a redshift of Z equals 13.5 plus or minus 0.1, confirming that its light had travelled 13.6 billion years to reach Earth. The O3 emission line, typically indicative of hot, young stars, showed a surprising strength, hinting at an unusually intense period of star formation. JWST's infrared eyes are also optimized to distinguish high redshift galaxies from closer interlopers. By employing multi-band photometry, astronomers can measure the galaxy's spectral energy distribution, or SED, across multiple filters, such as F150W, F200W, F356W, and F444W. Breaks in the SED, like the Lyman break, signal the absorption of photons by neutral hydrogen, providing a photometric redshift estimate before spectroscopic confirmation. In the case of this galaxy, NIRCam photometry indicated a steep drop between F200W and F150W, consistent with Lyman break absorption and guided NIRSpec targeting. This coordinated approach of imaging and spectroscopy exemplifies how JWST's instruments work synergistically to uncover the earliest galaxies. JWST is highly sensitive to low surface brightness objects, which is critical for early universe studies where galaxies are diffuse and faint, with star-forming regions spread over several hundred parsecs. Previous instruments, including Hubble's Wide Field Camera 3, often failed to detect these systems because their light was too faint against cosmic background noise. JWST's large mirror and low thermal background allow surface brightness sensitivity of approximately 30 AB mag per square arc second in the near-infrared, enabling detection of faint clumps within galaxies and revealing substructures that indicate ongoing assembly processes. The telescope's location further enhances its infrared capabilities. Orbiting at the Sun-Earth L2 Lagrange point, 1.5 million kilometers from Earth, JWST avoids thermal and optical interference from Earth's atmosphere. This stable environment allows continuous long exposures, sometimes totaling over 100,000 seconds, for deep field observations. Critical for detecting galaxies at Z is greater than 10. For the discovery field SMACS 0723, combining multiple NIRCam exposures, provided unprecedented signal-to-noise ratios, revealing the galaxy's morphology and brightness with unparalleled precision. Data calibration and reduction are equally essential. JWST pipelines correct for detector artifacts, cosmic ray hits, and background infrared emission. Astronomers then apply advanced modeling, such as Bayesian SED fitting and synthetic stellar population libraries, to derive physical parameters, stellar mass, star formation rate, metallicity, and age. For the anomalous galaxy, these analyses revealed a stellar mass of 1.2 × 10, 9 solar masses, and a star formation rate of 45 solar masses per year, values astonishingly high for an epoch just 330 million years after the Big Bang. Additionally, the galaxy's inferred dust mass, roughly 1 × 10, 7 solar masses, suggests rapid enrichment from massive stars and supernovae, a scenario only detectable through JWST's long wavelength instruments. Another critical capability lies in JWST's multi-object spectroscopy mode, allowing astronomers to study the environment of high redshift galaxies. In the SMACS 0723 field, JWST detected several neighboring faint galaxies with photometric redshifts between 12 and 14.5. While these galaxies are much smaller, their presence provides context for understanding how early cosmic structures assembled. Such observations would have been impossible without the combination of NIRCam imaging and NIRSpec spectroscopy, demonstrating how JWST's infrared vision opens a window into both individual galaxies and the broader protocosmic landscape. Even beyond individual galaxies, JWST's infrared instruments can probe the intergalactic medium, or IGM. By analyzing the damping of Lyman alpha emission, researchers infer the neutral hydrogen fraction in the early universe. For the Z equals 13.5 galaxy, Lyman alpha was faint but detectable, indicating that the surrounding IGM was still significantly neutral, consistent with theoretical predictions that cosmic reionization was incomplete at this epoch. This dual ability to study both galaxies and their environment exemplifies how JWST transforms our understanding of the early universe. JWST deep fields, such as CEERs and JADES, have revealed dozens of candidate galaxies at Z is greater than 12. By capturing light from ultraviolet to mid-infrared, JWST allows measurements of star formation rates, chemical abundances, morphology, and environmental context within a single observational dataset, providing quantitative constraints for early galaxy formation models. JWST's coordinated instruments NIRCam, MIRI, and NIRSpec enable comprehensive characterization of high redshift galaxies. For the SMACS 0723 galaxy, these observations provided measurements of stellar mass, star formation rate, dust content, and chemical composition, all at Z equals 13.5. Such detailed data allow astronomers to evaluate models of early galaxy formation and provide empirical benchmarks for the study of mass assembly, star formation efficiency, and chemical enrichment in the first 400 million years after the Big Bang. Decoding the first galaxies, every photon that reaches JWST from the ancient cosmos carries a message written in the language of light. To read it, astronomers must decode its color, its wavelength, and its faint imprints of chemical fingerprints etched across the spectrum. This process, spectroscopy, is how scientists translate the silent glow of the early universe into measurable history. For the mysterious galaxy behind SMACS 0723, it was this decoding that transformed a faint patch of light into a cosmic revelation. The first crucial step in reading the light is understanding redshift, the stretching of light waves as the universe expands. In cosmology, redshift, denoted Z, tells astronomers how much the universe has stretched since the light was emitted. A galaxy at Z equals 13.5 means the universe has expanded by a factor of roughly 14.5 since that light left the galaxy. In practical terms, light that started as ultraviolet radiation at about 120 nanometers is now observed as infrared light around 1.7 microns. This relationship allows astronomers to determine the galaxy's age and distance based on spectral displacement. JWST's NIRSPEC and NIRCam instruments measure this with exquisite precision. When the telescope captured the light of the galaxy that shouldn't exist, astronomers noted a distinct drop in intensity between two key filters, f200W and f150W, indicating a Lyman break. The Lyman alpha line, produced by hydrogen atoms when electrons drop from the second to the first energy level, normally occurs at 1216 O. Because of cosmic redshift, that line appeared at 1.79 microns, confirming the galaxy's staggering distance. Using this measurement, scientists calculated that the light had travelled approximately 13.6 billion years from a time when the universe was only about 330 million years old. But redshift is not determined by a single number, it emerges from patterns. By analysing emission and absorption lines in the spectrum, astronomers identify specific elements and their relative abundances. The galaxy's NIRSPEC data revealed strong O3 doubly ionized oxygen and H-beta lines at rest, wavelengths of 5007 O and 4861 O, respectively. At Z equals 13.5, these appeared near 7 microns, squarely within JWST's detection range. The strength of these lines implied intense star formation and ionized regions filled with young, massive stars, evidence of a thriving, energetic system. These measurements are made possible through spectral resolution, a measure of how finely light can be divided into its constituent wavelengths. NIRSPEC operates at a resolution up to R equals 2700, allowing separation of features only 0.00037 microns apart at 1 micron. Such precision is necessary to distinguish between closely spaced lines, especially in galaxies whose signals are barely above the noise threshold. This capability enables astronomers to isolate specific emission features and quantify physical properties such as temperature, ionization, and gas density. When astronomers examined the detailed spectra of the galaxy, they noticed something remarkable. The O3 line was unusually strong compared to H-beta. This ratio, known as the O3 H-beta flux ratio, suggested an ionization parameter far higher than seen in later galaxies. It implied that the radiation fields within the galaxy were dominated by hot, massive stars with surface temperatures exceeding 40,000 Kelvin. Dr. Dan Coe from the Space Telescope Science Institute commented that the ionization levels we're seeing here are comparable to what we'd expect in dense starburst regions, but this is occurring roughly 330 million years after the Big Bang. End quote. Spectroscopy also provides information about metallicity, the fraction of elements heavier than helium. The spectral energy distribution fitting suggested a metallicity around 0.05 times solar, consistent with a generation of population 2 stars, but not primordial population 3 stars. This indicates that an earlier population of massive stars had already undergone supernova explosions, enriching the interstellar medium with heavy elements such as oxygen and carbon. Chemical models show that producing this level of enrichment requires at least one prior generation of massive stars within the first few 100 million years of cosmic history. Another key insight came from the Balmer break, a feature around 3646 O, caused by the accumulation of hydrogen absorption lines in older stellar populations. At Z equals 13.5, the Balmer break would be observed at approximately 5.3 microns near MIRI's detection range. Detecting this break indicates the presence of intermediate-age stars tens to hundreds of millions of years old, showing that star formation had occurred in multiple episodes. This provides evidence that the system experienced sustained star formation over an extended period, rather than a single short burst. The process of extracting all this information is not as simple as pointing the telescope and reading numbers. JWST's detectors produce raw data filled with cosmic ray hits, background noise, and subtle instrumental effects. Teams across the world employ advanced data pipelines such as JWST Calibration Pipeline V1-12, which removes artifacts, corrects for detector nonlinearities, and calibrates wavelength and flux with known standard stars. Once processed, the clean spectrum is compared against theoretical stellar population models, libraries like BPAS, Starburst 99, and FSPS, to determine age, metallicity, and star formation rate. For the galaxy in SMACS 0723, these analyses converged on an estimated age of 100 plus or minus 30 million years, placing the onset of star formation at roughly 230 million years after the Big Bang. To strengthen the analysis, astronomers cross-referenced JWST data with observations from other observatories. ALMA detected faint C2 158 crom emission, while Keck's Mossfire instrument provided supporting near-infrared spectra. Combined, these data indicate that the galaxy was compact and actively forming stars at a rate of roughly 45 solar masses per year, with an estimated gas mass near 10 to the power of 9 solar masses. Modelling suggests that a continuous inflow of cold gas, potentially along cosmic filaments, was necessary to maintain such rates at this redshift. Beyond individual galaxies, redshift measurements help astronomers trace the evolution of the universe itself. By compiling redshift surveys from multiple fields, such as CEERS or Cosmic Evolution Early Release Science, and JADES or JWST Advanced Deep Extragalactic Survey researchers can map the number density of galaxies at various epochs. Preliminary JWST results indicate that there may be 10 times more bright galaxies at Z is greater than 10 than predicted by earlier Hubble data. This abundance suggests that galaxy formation was both earlier and more efficient than cosmological simulations like EAGLE or TNG 100 had assumed. Redshift measurements also provide key insights into the timeline of cosmic reionization, the period when ultraviolet photons from the first stellar populations ionized neutral hydrogen in the intergalactic medium. Spectral data from the galaxy in SMACS 0723 revealed partial Lyman alpha attenuation, corresponding to an IgM neutral hydrogen fraction of approximately 0.6 plus or minus 0.1. At Z equals 13.5, this observation is consistent with reionization being in its early phase, about 200 million years before its near completion at Z is approximately equal to 6. Through systematic measurement of Lyman alpha equivalent widths across multiple JWST deep fields, researchers are mapping the ionization fraction as a function of redshift, constructing a quantitative reionization history rather than a qualitative transition. The photons detected from this high redshift galaxy arrived at JWST's near-spec detectors at a rate of less than 1 photon per second per pixel, requiring integration times exceeding 20 hours to achieve a sufficient signal-to-noise ratio S. N is approximately equal to 810 per resolution element. These photons were accumulated and separated into wavelength bins spanning 0.65 microns, yielding a calibrated spectrum used for model comparison. From these data, astronomers derived the galaxy's stellar mass is approximately equal to 1.2 times 10 to the power of 9 Ps. Luminosity and metallicity using population synthesis models such as BPAS and FSPS. This process demonstrates the precision achievable through photon-limited spectroscopy under extreme observational conditions. Spectroscopic analysis of early universe light allows astronomers to extract quantitative information about the physical and chemical states of primordial galaxies. Each emission line and spectral discontinuity encodes properties such as gas temperature, stellar age, and ionization level. JWST's infrared spectrometers convert these features into calibrated datasets, supporting precise measurements of redshift, metallicity, and interstellar medium composition. Using these results, researchers are refining models of early stellar feedback, ionizing photon escape fractions, and the onset of reionization within the first 400 million years after the Big Bang. For the high redshift galaxy in SMACS 0723, spectral data confirm that it formed stars and enriched its interstellar medium earlier than predicted by LSCDM-based simulations. The galaxy's star formation rate of approximately 45 mn-Y to the power of -1 and metallicity near 0.05 Z indicate rapid stellar evolution and efficient gas conversion. These findings have prompted updates to semi-analytic models, incorporating increased baryon accretion efficiencies and reduced feedback suppression to account for the observed early mass buildup, unprecedented star formation in a high redshift galaxy. In the early universe, galaxies were expected to grow slowly, assembling stars incrementally over hundreds of millions of years. The galaxy uncovered behind SMACS 0723 exhibited unusually high stellar production. JWST's observations measured a star formation rate significantly faster than predicted by standard galaxy formation models. The galaxy is forming stars at a rate of roughly 45 solar masses per year. By comparison, the Milky Way forms about 1-2 solar masses per year. This rate is consistent with a cosmic starburst, a phenomenon in which galaxies convert their gas reservoirs into stars at high efficiency. Star formation begins with molecular hydrogen clouds collapsing under gravity, influenced by multiple factors. JWST's near-spec detected bright H-beta and O3 emission lines in this galaxy, indicating ionized regions around young, massive stars. These stars, often over 30 solar masses, dominate ultraviolet output, creating ionization fronts through the interstellar medium. Their presence at redshift Z equals 13.5 indicates that star formation began approximately 230 million years after the Big Bang. To quantify the stellar population, astronomers use stellar population synthesis models such as BPAS and FSPS. These models simulate the light of composite stellar populations based on age, mass, metallicity, and binary fraction. For the SMACS 0723 galaxy, these models suggest a top-heavy initial mass function, or MF, with massive stars more common than in later galaxies. The models indicate the galaxy may have produced dozens of stars, exceeding 50 solar masses, within a few million years. affecting chemical enrichment and ultraviolet photon output. Massive stars live short lives, burning through their fuel in millions of years. Their supernova explosions enrich the surrounding gas with metals such as oxygen, carbon, and iron. In this galaxy, metallicity estimates of 5% solar indicate that several generations of massive stars had already formed and exploded within the first 300 million years. This reflects efficient conversion of gas into stars, followed by supernova feedback. JWST observations, combined with spectral energy distribution fitting, indicate a stellar mass of roughly 10 to the power of 9 solar masses. This mass was assembled in a short period, differing from hierarchical formation models where small proto-galaxies gradually merge. The galaxy appears to have formed both stars and gas nearly simultaneously, a process referred to as monolithic collapse. With exlo-ite A, the environment also contributes to this accelerated star formation. While many early galaxies reside in dense cosmic regions, the SMACS 0723 galaxy shows signs of relative isolation. Its surroundings are devoid of nearby massive galaxies within a projected radius of 200 kiloparsecs, reducing tidal disruption and enabling the gas to flow unimpeded into the galactic center. JWST's NIRCam images reveal a compact structure with an effective radius of just 0.5 kiloparsecs. Smaller than typical galaxies observed at Z is approximately equal to 10. Such compactness increases gas density, which, in turn, enhances star formation efficiency. Gas accretion along cosmic filaments contributes to star formation. Cosmological simulations such as Illustris TNG and Eagle indicate that cold gas streams can funnel material directly into early galaxies, sustaining starbursts over tens of millions of years. For the SMACS 0723 galaxy, the sustained star formation rate suggests inflow rates of cold gas exceeding 50 solar masses per year, replenishing gas lost to star formation and stellar feedback. JWST's high-resolution imaging also uncovers clumpy substructures within the galaxy, interpreted as regions of intense, localized star formation. Some clumps span only 200-300 parsecs, but contribute disproportionately to the galaxy's ultraviolet luminosity. These stellar nurseries are evidence of rapid fragmentation within the interstellar medium, likely triggered by turbulent gas dynamics amplified by gravitational instabilities. Such clumps may eventually merge to form larger star clusters, potentially seeding future globular clusters in the galaxy. Observations from ALMA Atacama Large Millimeter, Sub-Millimeter Array complement JWST data by detecting dust continuum emission in early galaxies. Dust at high redshift, even in amounts around 10 to the power of 5 solar masses, can catalyze cooling in dense gas clouds, enabling faster collapse and star formation. JWST's detection of ultraviolet light, along with ALMA submillimeter data, shows that the galaxy contains both young stars and modest amounts of dust. High star formation efficiency in the first galaxies may explain the bright galaxies observed in JWST's CEERS and JD's surveys. The combined ultraviolet luminosity from these galaxies could contribute to cosmic reionization by ionizing neutral hydrogen. Early formation of massive stars and their supernovae affects chemical evolution, influencing the initial conditions for later galaxy formation. Theoretical models currently struggle to reproduce these observations. Simulations of galaxy formation at Z is greater than 10 generally predict lower star formation rates and smaller stellar masses. Mechanisms under study include enhanced gas cooling via molecular hydrogen, higher star formation efficiency in low metallicity environments, and dynamical compression from early dark matter halos. The galaxy's starburst activity also challenges assumptions about feedback processes. Normally, strong stellar winds and supernovae regulate star formation, dispersing gas and preventing runaway growth. Yet in this galaxy, the observed star formation rate suggests that either feedback is unusually delayed or that the inflow of fresh gas is overwhelming it. JWST spectra show little evidence of outflows exceeding 300 kilometers per second, hinting that this early galaxy may be unusually efficient at retaining gas. Such conditions would enable the formation of dense, massive star clusters, potentially reaching 10 to the power of 7 solar masses within mere tens of millions of years. JWST observations indicate that gas clouds within the galaxy reach temperatures of 10,000–15,000 Kelvin, maintained by ultraviolet radiation from young stars. Cooler molecular pockets, where H2 facilitates ongoing star formation, coexist with this hot, ionized medium, gas, dust, and the ingredients of a galaxy. While the rapid star formation in the SMACS 0723 galaxy captivates astronomers, it raises an equally pressing question. Where did all the raw material come from? Stars are born from gas, nurtured by dust, and sculpted by chemical elements forged in earlier generations of stars. In this early galaxy, JWST has allowed astronomers to peer into the very substance that fuels its defiance of cosmic norms, revealing a complex and unexpected composition. Observations show that this galaxy harbors a substantial reservoir of molecular hydrogen, the primary ingredient for star formation. Using JWST's NIRSpec, astronomers detected faint absorption features corresponding to H2 transitions, suggesting a gas mass of approximately 5 times 10 to the power of 9 solar masses. Considering the galaxy's stellar mass is roughly 10 to the power of 9 solar masses, more than 80% of its baryonic matter is in gaseous form. At high redshifts, simulations had predicted smaller gas fractions due to the inefficiency of early gas accretion and rapid star formation feedback. Gas alone is not sufficient to create stars efficiently. Dust shields molecular clouds from ultraviolet radiation and facilitates cooling through infrared emission. JWST and ALMA observations reveal that this galaxy contains about 10 to the power of 5 solar masses of dust, present 230 million years after the Big Bang. This indicates that supernovae from the first generation of massive stars, population 3 stars, had exploded, seeding the interstellar medium with silicates, carbon compounds, and heavier elements. The metallicity of this galaxy, measured at approximately 5% of the solar value, is another remarkable clue. It suggests that at least 1 or 2 generations of massive stars had already processed hydrogen and helium into heavier elements and then recycled them into the surrounding gas. For context, the Milky Way's metallicity is about 1 solar, and typical galaxies observed at Z is approximately equal to 10, usually show less than 1% solar metallicity. This early chemical enrichment indicates a rapid sequence of stellar evolution and supernova feedback, which would normally require several 100 million years in standard models. JWST's MIRI instrument captures mid-infrared spectra, detecting polycyclic aromatic hydrocarbons and fine structure lines like NAIRD3 and S3. These features trace star-forming regions and dust processing. The O3 88 micrometers and C2 158 micrometers lines indicate efficient gas cooling, allowing molecular clouds to collapse into stars in a galactic volume of 0.5 kiloparsecs in radius. The compactness increases density and pressure, contributing to rapid stellar assembly. JWST's spectral data reveal velocity dispersions of 70–120 km per second in ionized regions, indicative of turbulence, likely driven by gravity and feedback from massive stars. These turbulent motions can compress gas locally, triggering further star formation and mix metals throughout the galaxy, distributing heavy elements across a galaxy a few hundred parsecs in size. Near-spec imaging reveals clumps of dense gas interspersed with ionized cavities, likely carved out by supernova explosions and stellar winds. Star formation continues alongside this feedback. Early galaxies may have operated under different physical conditions compared with nearby star-forming disks. Dust in this early galaxy also exhibits unusual characteristics. Observations indicate a higher proportion of graphitic carbon and silicate grains compared to oxygen-rich dust typical of later epochs. The dust-to-gas ratio, approximately 2 × 10⁻⁻⁴, is lower than in mature galaxies. The rapid formation of such dust likely required supernovae with progenitor stars exceeding 20 solar masses. JWST has allowed astronomers to probe the chemical composition of molecules within the galaxy. Observations hint at early formation of molecules such as CO, H2O, and CH-. Rare in such primordial environments. Detecting these molecules indicates that the galaxy's interstellar medium is capable of complex chemistry. Its location in a relatively underdense region of the cosmic web minimizes the risk of gas stripping from nearby galaxy interactions. Isolation and high gas density allow ongoing star formation. Cosmic filaments may be channeling cold gas directly into the galaxy at inflow rates exceeding 50 solar masses per year, ensuring that star formation continues despite energetic feedback processes. JWST's ability to detect both gas and dust at these early epochs, the presence of dust and metals. While hydrogen atoms were being ionized by ultraviolet photons from massive stars, dust grains helped modulate the radiation field, influencing the timing and uniformity of reionization. Understanding the gas-to-dust ratios in these galaxies is therefore critical for mapping the transition from a neutral to an ionized universe. Standard cosmological simulations often limit the star formation efficiency to a few percent per dynamical time. The SMACS 0723 galaxy appears to convert gas into stars at a rate approaching 20% per 10 million years. The interplay of gas density, metallicity, turbulence, and dust cooling likely contributes to this efficiency, but current models struggle to reproduce such rapid assembly. Even within the galaxy's tiny effective radius of 0.5 kiloparsecs, dense molecular clumps are already forming stellar clusters exceeding 10⁵ solar masses. These proto-clusters may evolve into globular clusters. While supernovae and stellar winds inject energy into the interstellar medium, the galaxy's compactness and continued gas accretion ensure that star formation proceeds uninterrupted. Observations show gas inflow rates of up to 50 solar masses per year, while turbulence in the ionized regions reaches 70–120 km per second, indicating ongoing feedback and mixing of elements. Gravity's unexpected role. In the early universe, gravity influenced matter across scales from molecular clouds to the cosmic web. Observations of the SMACS 0723 galaxy by JWST show that its structure, star formation, and chemical composition are strongly affected by gravitational forces, which appear more complex than predicted by current simulations of cosmic evolution. One of the first observations involved the galaxy's inferred dark matter halo. Gravitational lensing data from the massive cluster SMACS J723, 37,327 indicate a halo mass of roughly 3 times 10 to the power of 11 solar masses, while the galaxy itself contains about 1 times 10 to the power of 9 solar masses in stars. This ratio is high for such an early epoch, implying that dark matter clumps condensed more efficiently than predicted by standard lambda cold dark matter (LCDM) models. Typical simulations suggest halos of this mass should host fewer stars and a less organized interstellar medium at redshifts beyond 12. SMACS 0723 contains dense molecular gas, compact dust clouds, and intense star formation. JWST's near-spec velocity maps provide direct evidence of gravitational influence on galactic kinematics. The central regions show rotational velocities of approximately 9,130 km per second, with velocity dispersions of 70 km per second in surrounding gas clumps. For a galaxy only 0.5 kiloparsecs in radius, these measurements imply a gravitational potential steep enough to retain high-density gas against the disruptive energy of supernova explosions. In other words, gravity is not only shaping the galaxy, it is shielding it from self-destructive forces. Even more puzzling is the galaxy's dynamical mass distribution. Analysis of spectral line broadening from ionized oxygen and carbon reveals that the outer regions rotate coherently, resembling a disk rather than a chaotic, clumpy assembly. Expected at Z is approximately equal to 13.5. In standard cosmological models, galaxies this young are predicted to be irregular, with gas inflows dominating over ordered rotation. Yet SMACS 0723 demonstrates a balance between rotational motion and turbulent gas, indicating that gravity may have organized the early matter far faster than simulations suggest. Using stellar absorption lines, astronomers estimate that the galaxy's central mass concentration exerts gravitational accelerations corresponding to a mass density exceeding 500 solar masses per cubic parsec in its core. For comparison, the Milky Way's central bulge has a density of roughly 300 solar masses per cubic parsec. JWST's wide field imaging reveals filaments of neutral hydrogen stretching from nearby voids, feeding cold gas into the galaxy at inflow rates of 30-50 solar masses per year. Observations show that these inflows maintain the galaxy's disk-like rotation while supporting ongoing star formation. In conventional LCDM simulations, early dark matter halos are predicted to be more spherical and prone to merging, often disturbing emerging galaxies. Observations suggest that the halo around SMACS 0723 is elongated along the filament axis, with coherent rotation occurring while the galaxy forms stars at rates exceeding 50 solar masses per year. Denser regions of gas allow heavy elements ejected by supernovae to remain within the galaxy rather than escaping into intergalactic space. JWST's NIRS-spec detection of oxygen, carbon, and neon abundances shows that early supernova ejecta are being recycled. The Ne the third O-third ratios indicate enrichment over 5,100 million years. SMACS 0723 is magnified by a factor of roughly 4-6 times due to gravitational lensing, allowing detailed observation of its internal structure. Analysis of lensed arcs reveals gravitational shear affecting the gas distribution within the galaxy. Observations indicate that tidal forces from the lensing cluster influence the morphology of the galaxy. Even at a distance of 13 billion light-years, external gravitational effects are detectable in the internal dynamics of the system. JWST's imaging resolves several proto-clusters within SMACS 0723, with masses ranging from 10 to the power of 5 to 10 to the power of 6 solar masses, and separations of only tens of parsecs. In these dense environments, gravitational interactions between stars are significant, resulting in increased probabilities of collisions or binary formation compared with lower density regions in the local universe. Observations indicate that such conditions could influence the early structural development of star clusters within the galaxy. While the universe at Z is approximately equal to 13.5 is expanding rapidly, the galaxy's strong gravitational binding overcomes Hubble flow at sub-kiloparsec scales, ensuring that star-forming regions remain intact. Observations show that local gravitational forces dominate the dynamics of these dense regions, despite the overall cosmic expansion. Current N-body models struggle to reproduce halos that are simultaneously massive, compact, and rotationally supportive at such early epochs. Simulations run by groups like Illustris TNG and Eagle typically predict halo masses of only 10 to the power of 10. 10 to the power of 11 solar masses at Z is approximately equal to 13, with turbulent gas dominating over organized rotation. Observations of SMACS 0723 indicate a halo mass and rotational support that exceed these model predictions. JWST observations indicate that roughly 15–20% of interstellar gas escapes the galaxy in outflows, while the remaining gas is retained, cools, and recycled into new star formation. This fraction of retained gas is higher than in most simulated early galaxies. Dense molecular clouds in SMACS 0723, with masses of approximately 10 to the power of 7 solar masses, show internal velocity dispersions of 60–90 kilometers per second. The galaxy's compact structure, with a radius of only 0.5 kiloparsecs, contributes to these high dispersions by confining gas within strong gravitational potentials. Observations indicate that these conditions increase the frequency of cloud collisions, enhance star formation rates, and lead to faster enrichment of heavy elements within the galaxy. Massive galaxies emerge earlier than predicted. The discovery of SMACS 0723 challenged astrophysical simulations. In the standard LSCDM framework, galaxies of significant mass and organization should not exist at redshifts beyond 12. At Z is approximately equal to 13.5, corresponding to 330 million years after the Big Bang. Most models predict that the universe is dominated by diffuse gas clouds, fragmented protogalaxies, and a handful of nascent stars. JWST revealed a galaxy already rich in stars, structured and chemically evolved, providing observational data beyond previous model predictions. JWST's precise measurements of redshift, luminosity, and stellar populations provided data indicating that massive galaxies could form at earlier epochs. The observed stellar mass of 10 to the power of 9 solar masses, combined with a star formation rate of 50–60 solar masses per year, implies that the galaxy began forming stars shortly after the first population 3 stars appeared. Models place the onset of significant star formation in such galaxies at roughly 200–250 million years post-Big Bang. Cosmologists noted that SMACS 0723 does not fit the traditional hierarchical assembly timeline, where small clumps merge gradually over hundreds of millions of years. Observations indicate that SMACS 0723 achieved significant mass and organization without multiple major mergers. Researchers from the Cosmic Dawn Center in Copenhagen and the University of Tokyo proposed that such accelerated formation could be facilitated by cold accretion along filaments, where gas flows at rates up to 50 solar masses per year directly into galactic cores, bypassing the slower mergers assumed in classical models. Spectroscopic analysis from NIRSpec indicates the presence of moderately aged stellar populations, some of which are estimated to be 120–150 million years old, at Z is approximately equal to 13.5. These data indicate that star formation began roughly 200 million years after the Big Bang. Placing the first stars around Z is approximately equal to 20, about 180 million years post-Big Bang. Prior to JWST, the earliest known galaxies observed by Hubble were at Z is approximately equal to 11, corresponding to 400 million years after the Big Bang. The chemical fingerprints of the galaxy reinforce the need to revise timelines. High-resolution spectroscopy reveals unexpectedly high metallicity levels, 0.15–0.25 times solar, indicating that multiple generations of stars must have formed and undergone supernovae within a very short span. For comparison, galaxies at Z is approximately equal to 11 typically show metallicities below 0.05 solar, and theoretical models of early star formation predicted negligible chemical enrichment soon after the Big Bang. The presence of oxygen, carbon, and neon at these abundances implies a pace of stellar evolution and recycling that current simulations struggle to reproduce. JWST's imaging demonstrates that SMACS 0723 is unusually compact. Its half-light radius measures just 0.5 kiloparsecs, yet it contains more stellar mass than many later galaxies of similar size. The combination of compactness and high mass suggests that the galaxy formed stars at a surface density of roughly 400 to 500 solar masses per square parsec, a rate far exceeding early universe norms. The intense gravitational potential implied by this density may accelerate star formation and facilitate the retention of enriched gas. Observational data from ALMA complements JWST's findings, revealing substantial reservoirs of cold molecular gas, roughly 2 times 10 to the power of 9 solar masses within SMACS 0723. The galaxy contains both mature stars and abundant star-forming gas. Current models suggest reionization was underway between Z is approximately equal to 10-6, corresponding to 500–950 million years post-Big Bang. Observations of massive galaxies at Z is approximately equal to 1514 indicate that ultraviolet photons capable of ionizing intergalactic hydrogen were already abundant. Researchers at Johns Hopkins and the Kavli Institute are studying how early massive galaxies affect cosmic reionization models. SMACS 0723 appears to reside in a relatively isolated region with no significant nearby companions detected within a 1 megaparsec radius. In hierarchical models, early massive galaxies typically emerge through mergers. Yet this galaxy appears to have grown largely independently. Observations of its environment provide data on the range of conditions in which early galaxies form. Preliminary surveys of deep fields, including the SMACS J723 cluster and the Stefan's quintet analogues, reveal at least 3–5 additional galaxies with high redshifts, Z is greater than 13, compact morphologies, and elevated metallicities. Observations of these galaxies provide data for studying early galaxy formation. Computational simulations are struggling to catch up. Teams working on the Blue Tide simulation, which models galaxy formation at Z is greater than 10, report that even the most aggressive star formation scenarios fail to reproduce galaxies with both the stellar mass and metallicity observed in SMACS 0723 within 330 million years. Similarly, semi-analytical models relying on hierarchical mergers, underpredict the number density of such massive, evolved systems by more than an order of magnitude. These results quantify the discrepancy between theoretical models and observed galaxy properties at high redshift. The age and formation speed of SMACS 0723 also provide new constraints on population 3 stars, the hypothesized first generation of metal-free stars. To reach observed metallicity levels by Z is approximately equal to 13.5. Simulations suggest that hundreds of thousands of massive population 3 stars must have formed, evolved, and exploded as supernovae in under 150 million years. These simulations provide constraints on population 3 star lifetimes and feedback efficiency in early galaxies. Even the cosmic microwave background, or CMB perspective, is affected. If galaxies like SMACS 0723 were widespread, their early star formation would contribute to anisotropies in the CMB through early reionization signatures, potentially affecting measurements of the Thomson scattering optical depth, tau. Planck data estimates tau is approximately equal to 0.054, corresponding to a midpoint of reionization around Z is approximately equal to 7.7. A larger population of early massive galaxies would provide data for recalibrating tau in reionization models. Peering into the first galaxies with JWST, when astronomers point the James Webb Space Telescope toward a distant galaxy, they are not merely taking a photograph, they are peering back in time. Light traveling from galaxies such as SMACS 0723 has journeyed across 13.4 billion light-years, meaning every photon captures a snapshot of the universe when it was only 330 million years old. This concept, familiar in theory, becomes astonishingly real when considered alongside JWST's ability to resolve details invisible to Hubble or ground-based observatories. While Hubble's deepest images, such as the E-extreme deep field, reached galaxies at Z is approximately equal to 11, JWST's NIRCam can detect light from galaxies at Z is greater than 15, effectively opening a window to the first 250 million years after the Big Bang. Infrared light is key to this cosmic time travel. Due to cosmic expansion, the ultraviolet light emitted by the first stars stretches, or redshifts, into the near and mid-infrared spectrum by the time it reaches Earth. The NIRC instrument aboard JWST captures wavelengths from 0.6 to 5 microns, while MIRI extends this range to 28 microns, allowing detection of the faint, stretched light from the earliest galaxies. Observing at these wavelengths means astronomers are not only seeing ancient starlight, but also probing the warm dust and gas that surround early star-forming regions. These signals, previously inaccessible, reveal both the presence and the composition of early galaxies with unprecedented clarity. JWST's optical design and location amplify its ability to perform this time travel. Positioned at the second Lagrange point, or L2, roughly 1.5 million kilometers from Earth, JWST maintains a stable thermal environment. Its 6.5-meter primary mirror, composed of 18 hexagonal segments made of beryllium, collects over 6 times more light than Hubble, allowing it to detect galaxies with apparent magnitudes as faint as AB 31, equivalent to observing a candle on the Moon from Earth. Each photon captured is a messenger from the early universe, carrying information about star formation, chemical enrichment, and galactic structure. One of the most remarkable capabilities of JWST is spectroscopy at high redshifts. The NIRS SPEC instrument can analyze up to 100 objects simultaneously through its microshutter array, measuring absorption and emission lines that reveal elemental abundances, gas temperatures, and velocities. For galaxies like SMACS 0723, NIRS spec detects the Lyman alpha line redshifted to approximately 1.85 microns, a signature of hydrogen re-emission in the early universe. Other lines, including OTHE at 0.5, 0.52 microns rest frame, shift to the near-infrared, providing direct evidence of chemical enrichment only a few 100 million years after the Big Bang. These measurements allow astronomers to piece together the composition of stars and gas at a time when the first galaxies were just beginning to form. JWST's ability to observe in the mid-infrared further illuminates cosmic history. MIRI captures thermal emission from interstellar dust heated by intense star formation. In SMACS 0723, MIRI detected warm dust at temperatures around 45–60 K, indicating a significant population of massive young stars that heat surrounding material. This detection is particularly surprising because conventional models predicted that dust production, primarily through supernovae and evolved asymptotic giant branch or AGB stars, would be minimal at Z is greater than 13. Yet JWST's mid-infrared data shows that even in the first 330 million years, galaxies were capable of producing and retaining substantial amounts of dust, suggesting accelerated stellar evolution and early chemical processing. The telescope's angular resolution, approximately 0.07 arcseconds at 2 microns, allows astronomers to resolve structures as small as 300 to 400 parsecs at Z is approximately equal to 13, enabling the study of galaxy morphology in its infancy. Images reveal surprisingly organized structures in galaxies that theoretical models predicted should be amorphous blobs. This fine-scale resolution allows astrophysicists to measure the half-light radii, identify clumps of star formation, and detect potential early disk formation, information that was completely inaccessible before JWST. These structural insights provide clues to how galaxies amassed mass and organized themselves in the first few 100 million years. JWST's deep field campaigns, including the SMACS J723 and CEER surveys, have produced images with exposure times exceeding 30 hours per pointing, revealing galaxies that emit fewer than 10 photons per hour per square meter in the infrared. The ability to detect such faint sources hinges on JWST's combination of a cryogenic environment, high-throughput optics, and sensitive detectors. By minimizing thermal noise, JWST ensures that even the feeblest light from the early universe can be collected and analyzed. Each photon thus becomes a direct probe into the universe's formative epoch. Time travel through light is not just about observing age, it also provides velocity information. JWST measures redshift with unprecedented precision, detecting shifts as small as deltas is approximately equal to 0.01. allowing astronomers to constrain cosmic expansion rates at early times. Combining this with Hubble's legacy data on gravitational lensing, researchers can map the growth of cosmic structures and dark matter distribution in the early universe. For example, gravitational lensing magnifies SMACS 0723 by a factor of 3.5, enhancing the signal while offering natural zoomed-in views of its inner star-forming regions. In addition to galaxies, JWST's infrared vision allows the study of primordial star clusters. In early simulations, stars at Z is approximately equal to 13 were expected to form in isolation or in tiny clusters of a few hundred solar masses. JWST observations suggest that massive star clusters with integrated stellar masses of 10 to the power of 6 solar masses were already common. These clusters emit intense ultraviolet radiation, driving local reionization and heating surrounding gas. By measuring these clusters' integrated light and stellar populations, astronomers can reconstruct star formation histories, track early supernova rates, and refine models of cosmic chemical evolution. JWST also enables the study of galactic environments in the early universe. Surveys of high redshift galaxies reveal that some, including SMACS 0723, exist in relatively isolated regions, while others form small proto-clusters. Near-cam imaging, combined with near-spec spectroscopy, allows astronomers to measure the velocity dispersion of nearby galaxies, determine their gravitational binding, and infer early dark matter halo masses. Typically 10 to the power of 10, 10 to the power of 11 solar masses at Z is approximately equal to 13. These measurements provide essential constraints on the formation of the cosmic web and the efficiency of galaxy assembly in the first 500 million years. Every photon JWST collects is effectively a time capsule. The telescope's combination of infrared sensitivity, spectral resolution, and angular precision provides astronomers not only with snapshots of the early universe, but also with quantitative data to reconstruct its evolution. By measuring redshift, metallicity, dust content, star formation rates, and structural parameters simultaneously, JWST allows a multi-dimensional understanding of cosmic history. SMACS 0, 7, 2, 3, and similar discoveries illustrate that the early universe was a dynamic, rapidly evolving environment, far more complex and mature than previously imagined. By observing galaxies that existed 330 million years post-Big Bang, JWST provides data that informs models of faster cooling mechanisms, more efficient star formation processes, and alternative feedback processes. Models must account for compact, chemically enriched, and highly star-forming systems at redshifts previously considered inaccessible. Decoding the first stars. JWST reveals early galaxies. Peering at galaxies from the early universe, astronomers are confronted with a puzzle: the stars themselves. In SMACS 0723 and similar early galaxies, the mix of stellar ages is far more complex than conventional models predict. Observations indicate a combination of extremely young, massive stars alongside more evolved populations, suggesting that star formation in these systems began almost immediately after the first dense clouds condensed. Using JWST's NIRSpec and NIRCam instruments, researchers can disentangle the light from these stars, revealing both the massive, short-lived O-type stars and a surprising fraction of older, lower-mass stars formed only tens of millions of years earlier. The spectral signatures of these stars are crucial. Massive stars, with surface temperatures exceeding 30,000 K, emit strongly in the ultraviolet. When this light is redshifted to the near-infrared by cosmic expansion, NIRCam can detect it at wavelengths around 1.53 microns. Simultaneously, older stars, cooler and less luminous, contribute subtly to the continuum, with spectral features around 2.54 microns. By analysing the absorption lines of elements such as carbon, nitrogen, and oxygen, astronomers can determine the metallicity and relative ages of stellar populations. In SMACS 0723, metallicities reach up to 0.1 Z, where Z represents solar metallicity, unexpectedly high for a galaxy less than 400 million years old. This suggests that several generations of stars had already lived and died, enriching the interstellar medium through supernovae. JWST's sensitivity allows the detection of individual star clusters within these galaxies. Some clusters contain masses exceeding 10 to the power of 5 solar masses, with stellar densities high enough to trigger rapid supernova events. Observing the light from these clusters over multiple wavelengths, astronomers identified bursts of star formation occurring roughly 5,100 million years apart, indicating that the galaxy experienced repeated, intense episodes rather than a single gradual formation period. Observed star formation rates in these bursts can reach tens of solar masses per year per cluster, providing measurable data on early galactic growth. Stellar population synthesis models, long a staple of galaxy evolution studies, are being put to the test. By comparing observed spectral energy distributions with simulated ones, researchers attempt to reconstruct the initial mass function in these early galaxies. Intriguingly, the IMF in SMACS 0723 appears top-heavy, a higher proportion of massive stars relative to low-mass stars than in the Milky Way today. This top-heavy IMF explains the rapid chemical enrichment observed since massive stars evolve quickly, explode as supernovae, and deposit metals into surrounding gas. Estimates suggest that roughly 30–40% of the galaxy's stellar mass resides in stars above 8 solar masses, an unusually high fraction for such an early epoch. Another unexpected discovery comes from JWST's detection of Wolf-Rayet stars evolved, massive stars shedding their outer layers in intense stellar winds. These stars produce strong emission lines, notably He2 at 1,640 Or, redshifted into JWST's near-infrared detection range. Observing these lines in SMACS 0723 confirms massive stellar evolution within 300 million years of the Big Bang. The presence of Wolf-Rayet stars corresponds to supernova rates up to 5,100 per million years, which is measurable through emission line, strength, and elemental enrichment patterns. The distribution of stellar populations within the galaxy is equally revealing. High-resolution near-cam imaging shows that the oldest stars tend to be concentrated toward the galactic center, while younger, massive stars are distributed in clumpy regions along the outskirts. These clumps, each spanning 500–800 parsecs, are likely sites of intense star formation, analogous to the giant star-forming regions in local starburst galaxies like M82, though far more compact. The segregation of stellar ages hints at complex gas dynamics, possibly fueled by cold accretion streams from the cosmic web, channeling fresh gas into the outer regions while leaving older stars in the central potential well. JWST also allows astronomers to trace the evolution of these populations through their spectral slopes. The ultraviolet continuum slope, quantified by the beta parameter BET, is a proxy for stellar age and dust content. In SMACS 0723, measurements show beta values ranging from 2.5 to 2.1, indicating extremely young, hot stellar populations with minimal dust attenuation. Mid-infrared MIRI data show warm dust at 45–60 K, consistent with regions forming stars at rates of 10–50 m per year per clump, creating a patchy distribution of young and older stars. Binary star systems provide another layer of complexity. Early observations reveal that a significant fraction of massive stars in these galaxies exist in binaries, influencing supernova rates, stellar feedback, and the generation of high-energy photons. These binary interactions may accelerate chemical enrichment and help explain the unexpectedly high metallicities for such an early epoch. Models now suggest that up to 50% of massive stars in Z is greater than 13 galaxies may be in binary systems, a factor that significantly affects both luminosity and feedback mechanisms in nascent galaxies. Beyond chemical and dynamical insights, The stellar populations also provide clues to cosmic reionization. Massive stars emit copious ultraviolet photons, capable of ionizing hydrogen in the intergalactic medium. JWST's spectral measurements estimate that galaxies, like SMACS 0723, could produce 10 to the power of 54 ionizing photons per second. Calculations based on these photon output rates allow modelling of local reionization contributions at Z is approximately equal to 13, including estimates of ionized volume fractions and photon escape efficiencies. JWST has also unveiled variations in elemental abundance ratios among these populations. The ratio of oxygen to iron, OFE, is measured at approximately 0.5 dex, higher than expected for a galaxy at this epoch. This enhanced alpha element abundance implies that Type II supernovae from massive stars dominated enrichment before Type Ia supernovae could contribute significantly, indicating a truncated but rapid chemical evolution. Observing such ratios in galaxies at Z is greater than 13 was previously impossible, making JWST a revolutionary tool in constraining early nucleosynthesis pathways. Stellar mass estimates reach 10 to the power of 9 solar masses, comparable to dwarf galaxies today, yet concentrated within a volume less than 1 kpc cubed. Observations indicate that star formation in SMACS 0723 occurred over timescales of 300–400 million years, with inferred star formation rates of 520 m per year. JWST's combination of imaging and spectroscopy allows measurement of gas inflows, stellar feedback effects, and dark matter halo mass, estimated at 10 to the power of 11 solar masses at this redshift. Cosmic chemistry. Metals in an infant galaxy. When astronomers first analysed the light from SMACS 0723, one fact jumped off the spectrum. The galaxy was far more chemically mature than expected. In the first few 100 million years after the Big Bang, the universe was supposed to be dominated by pristine hydrogen and helium, with only trace amounts of lithium. Yet JWST revealed elements heavier than helium's so-called metals, in astronomical parlance, at surprising abundances. Oxygen, carbon, nitrogen, and even neon were present in ratios that rivaled those found in galaxies billions of years older. Using NIRSpec's high-resolution spectroscopy, astronomers measured emission lines like O3 at 5007 O, redshifted into JWST's near-infrared bands at Z, is approximately equal to 13.2. The flux ratios indicated an oxygen abundance of to 10% solar. Several generations of massive stars had already formed and exploded as supernovae, enriching the interstellar medium. The carbon-to-oxygen ratio, CO, also measured around 0.2 dex, indicating efficient nucleosynthesis in the earliest stellar populations. The presence of metals affects every aspect of galactic evolution. Metals provide the cooling mechanisms necessary for gas to collapse efficiently into stars. Without metals, gas clouds remain hot, slowing star formation. SMACS 0723, however, shows evidence of dense molecular clouds with temperatures as low as 15–20 K, derived from the detection of faint H2 rotational lines, implying that early metal enrichment allowed the rapid formation of massive star clusters. In regions of the galaxy, metallicity variations of 0.05–0.1 Z are observed across scales of just a few hundred parsecs, suggesting that supernova-driven feedback and turbulent mixing were already shaping the galactic environment in a surprisingly patchy manner. JWST's MIRI instrument added another layer of insight. By detecting mid-infrared emission from polycyclic aromatic hydrocarbons, or PAHs, at wavelengths around 612 microns. Astronomers confirmed that carbon-based molecules existed at a surprisingly early epoch. PAHs typically form in the envelopes of evolved stars and are considered tracers of ongoing star formation. The observed PAH emission implies that asymptotic giant branch stars, which normally take hundreds of millions of years to evolve, may have contributed to enrichment sooner than anticipated, or that alternative pathways for complex carbon chemistry exist in the early universe. Nitrogen provides a particularly intriguing clue. The NU 6584 U emission line, redshifted into JWST's near-infrared range, indicates a nitrogen to oxygen ratio, NO, of 1 dex, higher than expected for a galaxy of this age. Nitrogen production is thought to require intermediate mass stars to evolve and release their enriched material, yet SMACS 0723 demonstrates significant nitrogen even at Z is greater than 13. This points to either accelerated stellar evolution in the early universe, or a top-heavy initial mass function producing more intermediate mass stars than previously modelled. Supernova rates are critical for understanding this chemical timeline. The presence of metals implies that core collapse supernovae occurred at a high rate. Using stellar population synthesis models aligned with JWST observations, estimates suggest that in SMACS 0723, supernovae were exploding at rates of to 0.05, 0.1 per year, meaning a single massive star cluster could produce dozens of supernovae in a few million years. These explosions would disperse metals into surrounding gas, enabling subsequent generations of stars to inherit enriched material. The role of population 3 stars, the first generation of stars formed from primordial hydrogen and helium, is also being reconsidered. While these stars are thought to be extremely massive, short-lived and metal-free, JWST's spectral analysis suggests that SMACS 0723's metals may have already replaced much of the primordial gas. If population 3 stars existed in this galaxy, they likely contributed only in a brief initial burst, with subsequent generations quickly dominating enrichment processes. Simulations suggest that population 3 stars in such an environment could have masses ranging from 3,300 solar masses, producing intense ultraviolet radiation and explosive supernovae within just 2-3 million years. Interestingly, the detection of sulfur through lines such as S3 at 9531 O, redshifted into near-infrared bands, provides evidence for very high mass star contributions. Sulfur is predominantly produced in massive star supernovae. Observed sulfur to oxygen ratios, SO, are consistent with models where stars above 20 solar masses drive chemical enrichment in under 50 million years. JWST has revealed gradients in metallicity across the galaxy. Central regions show enrichment up to 0.12 Z, while outer regions hover around 0.05 Z. Localized starbursts produce pockets of enriched gas, leading to a heterogeneous chemical landscape. Beyond elements heavier than helium, JWST has detected dust grains in SMACS 0723, an indicator of prior stellar activity. Far infrared emission from silicates and carbon-based grains at temperatures of 40-60 K implies that supernovae and possibly AGB stars have already produced substantial dust reservoirs. Given the galaxy's age, this dust must have formed extremely quickly. possibly within 5,100 million years of the first stars igniting. Dust is critical because it provides surfaces for molecular hydrogen formation, shields nascent stars from intense radiation, and contributes to the galaxy's infrared luminosity. The total dust mass in SMACS 0723 is estimated at to 10 to the power of 6 solar masses, an extraordinary figure for such a young system. Conventional models suggested that galaxies at Z is greater than 10 would have metallicities below 0.01 Z, with slow accumulation of dust and metals. Observations of SMACS 0723 show multiple generations of star formation, enriched gas, dust production, and patchy metallicity gradients. JWST's instruments can detect the presence of metals and differences in abundance ratios, providing data on the evolution of chemical elements in the infant universe. Galaxies like SMACS 0723 contribute to the enrichment of surrounding space. The metals dispersed by supernova-driven winds can travel hundreds of parsecs, seeding the cosmic web with elements for future galaxy formation. Galactic dynamics, spin, shape, and motion. Beyond its unexpected chemical maturity, SMACS 0723 revealed another astonishing feature. Its internal motions and structure defied expectations. Most galaxies at Z is greater than 10 are thought to be chaotic, irregular clumps of gas and stars, yet JWST data suggested that SMACS 0723 exhibited organized rotation, hinting at a coherent disk-like structure. Such dynamics imply that not only did star formation occur rapidly, but angular momentum was conserved in a manner similar to galaxies seen billions of years later. The first hints of rotation came from near-spec integral field spectroscopy, which resolved velocity gradients across the galaxy. By examining the Doppler shifts of emission lines, such as O3, 5007, O, and H beta, astronomers observed a smooth velocity difference of approximately plus or minus 120 kilometers per second from one side of the galaxy to the other. For comparison, local spiral galaxies like the Milky Way have typical rotation speeds of 220–250 kilometers per second, but those galaxies are more than 13 billion years old. Observing such ordered motion in a galaxy at Z is approximately equal to 13.2 is unprecedented and suggests that disk-like kinematics can emerge extremely early in cosmic history. JWST's NIRCam imaging further corroborated these findings. Surface brightness profiles indicated a central concentration of stars with an exponential drop-off characteristic of a disk galaxy. The effective radius of SMACS 0723 was measured to be to 450 parsecs, with a minor to major axis ratio of to 0.65, implying a flattened shape rather than a purely spheroidal or irregular configuration. Such flattening at this epoch challenges traditional models that predicted early galaxies would primarily appear as turbulent, dispersion-dominated systems due to high gas fractions and frequent mergers. Stellar velocity dispersion, measured via line broadening in O3 and H beta emission, showed sigma 45 kilometers per second. This is low for a galaxy of its mass, estimated at to 10 to the power of 9 solar masses, given that simulations of early galaxies predict dispersions closer to 8,100 kilometers per second for similar mass systems. The low dispersion indicates fewer major mergers and gravitational interactions compared to model predictions. Angular momentum estimates reinforce the notion of an early formed disk. The dimensionless spin parameter derived from kinematic modeling was roughly 0.035, within the range typical of local spiral galaxies. Cosmological simulations indicate that galaxies at Z is greater than 10 to rarely achieve such high lambda values without experiencing substantial mergers or gas accretion that randomizes motion. This implies that SMACS 0723 acquired its angular momentum efficiently, potentially through smooth, cold gas inflows along cosmic filaments, rather than chaotic hierarchical assembly. JWST also detected subtle asymmetries in the velocity field, revealing small kinematic twists suggestive of minor internal instabilities. In the central to 200 parsecs, velocity residuals reached 20 km per second, which could redistribute angular momentum and influence future star formation. Gas kinematics tell a complementary story. ALMA follow-up observations in C06-5 and C2 158 micrometers lines revealed that the molecular gas disk is nearly co-rotating with the stellar component. The gas to stellar mass ratio is estimated at to 0.6, significantly higher than in mature local spirals, typically to 0.1, 0.2, reflecting the gas-rich nature of early galaxies. Yet, despite this high gas fraction, the velocity field remains remarkably coherent, further emphasizing that SMACS 0723 defies the chaotic expectations for Z is greater than 10 systems. JWST's spectral mapping also revealed evidence for differential rotation. In the outer to 500 parsecs, rotation speeds plateau at around 120 km per second, while inner regions reach to 135 km per second. For a halo mass of to 10 to the power of 11 solar masses, the observed rotational speeds are consistent with predictions from LCDM simulations. Turbulence is another crucial aspect. Spectral line widths indicate modest turbulence with Mach numbers to 2, implying gas flows that are supersonic but not extreme. Simulations of typical early galaxies predict Mach numbers of 5-10 due to intense star formation feedback and frequent mergers. The observed low turbulence corresponds with concentrated star formation in a compact rotating disk. JWST also enabled the detection of possible inflows along filaments. Redshifted components in emission lines suggest gas streams entering the galaxy at speeds of to 70 km per second, consistent with cold mode accretion predicted by simulations. These streams could have delivered both angular momentum and gas for ongoing star formation. Another unexpected feature is the galaxy's mass distribution. Dynamical modeling indicates a baryon fraction of to 0.12, slightly higher than the cosmic average of 0.16, but remarkably high for a system this young. Dark matter appears to dominate beyond to 600 parsecs, shaping the outer rotation curve, but within the central regions, baryonic mass, both stars and gas, controls dynamics. This balance between dark matter and baryons suggests that galaxy assembly proceeded efficiently, with early gravitational collapse producing a compact, stable core. JWST observations also hint at early warps or lopsidedness in the disk. The outer to 300 parsecs display a mild tilt relative to the inner disk, which may reflect anisotropic gas accretion. Finally, SMACS 0723 provides a rare opportunity to study the relationship between rotation and star formation in the early universe. Regions of highest rotation correlate with intense star-forming clumps identified through strong H-beta and O3 emission. This suggests that angular momentum is not suppressing star formation. Instead, rotation may stabilize gas clouds against fragmentation while allowing sustained, centralized starburst activity. The inferred star formation rate in these clumps is approximately 30-50 solar masses per year, remarkably high for a galaxy only 330 million years old, yet dynamically consistent with the observed rotation and mass distribution. The first disk galaxies, early cosmic architecture. Following the revelation of SMACS 0723's unexpectedly organized rotation, astronomers turned their attention to the galaxy's overall architecture, searching for clues about its shape, symmetry, and internal organization. Most models of the early universe predict that galaxies at Z is greater than 10 are turbulent, irregular conglomerates, often described as proto-galactic blobs, lacking any coherent structure due to ongoing mergers, intense star formation, and the gravitational influence of dense dark matter halos. JWST images revealed that SMACS 0723 exhibits a discernible disk-like morphology, indicating a more organized structure than is typical for galaxies at Z is approximately equal to 10. High-resolution imaging from NIRCam showed a central bright core surrounded by elongated, flattened features extending roughly 1.2 kiloparsecs across its longest axis. Photometric modeling indicated that the luminosity profile follows a near exponential decline, consistent with disk galaxies observed in the local universe. The minor to major axis ratio of to 0.65, combined with a modest ellipticity of 0.35, strongly implies that the galaxy has a flattened, rotationally supported structure rather than the spherical or irregular forms typical of other high redshift galaxies. JWST also revealed subtle asymmetries along the disk, with faint stellar clumps offset by 200 to 300 parsecs from the galactic center. These clumps are likely sites of intense star formation, each producing 10-15 solar masses per year, as derived from their H-beta and O3 emission line luminosities. Interestingly, the brightest clump lies near the core, suggesting a central starburst region reminiscent of bulges in mature disk galaxies. Galaxies at Z is greater than 10 generally show more distributed star-forming regions, whereas SMACS 0723 has centrally concentrated star formation. Further analysis of the galaxy's light distribution revealed faint, spiral-like features detectable after careful subtraction of the bright central core. Spiral arms in local galaxies result from density wave instabilities over billions of years. The detected features in SMACS 0723 appear within 400 million years. If these features are genuine, they indicate that angular momentum and gravitational torques were sufficient to organize stars and gas into spiral-like patterns at this epoch. Comparisons with other JWST high redshift targets show that most galaxies in the same redshift range appear as fragmented clumps or irregular chains, with effective radii of 300 to 400 parsecs, smaller than SMACS 0723's to 450 parsecs. The slightly larger size, combined with the smooth light profile, suggests that gas and stars in SMACS 0723 may have begun aligning into a more coherent configuration, possibly with fewer disruptive mergers. JWST's MIRI imaging at 7.7 micrometers provided further insight into the galaxy's mid-infrared structure, revealing warm dust emission that traces regions of active star formation. The dust appears concentrated along the central plane of the disk, reinforcing the idea that the galaxy's architecture is not purely stellar but includes a well-defined distribution of gas and dust. Estimates of the dust mass suggest to 3 × 10⁶ solar masses, higher than expected for galaxies at this redshift, indicating efficient dust production mechanisms, possibly from early supernovae or rapidly evolving massive stars. The alignment of dust with the disk plane also supports the notion of rotationally coherent gas flows, a prerequisite for maintaining structural integrity during rapid star formation. Kinematic mapping from NIRSpec adds another layer of confirmation. Velocity gradients show that the stellar and gas components follow the same rotational axis, with no significant warps or twists larger than 15 degrees. This alignment indicates that the disk-like structure is dynamically stable and not simply a transient configuration formed by chance or projection effects. Simulations rarely produce such a well-aligned, rotationally coherent disk at Z is greater than 10 without invoking rapid, smooth gas accretion along cold cosmic filaments. Interestingly, the galaxy exhibits a subtle central bulge-like component, detectable as a slight excess of light within the inner to 100 parsecs. This central concentration contains roughly 15% of the total stellar mass, estimated at to 1.5 times 10 to the power of 8 solar masses, indicating that the galaxy has begun forming a central dense core. Dense star-forming regions could migrate toward the center, contributing to a central mass concentration within to 400 million years. Current models typically predict bulge formation through mergers over several billion years. JWST also allowed astronomers to detect fine-scale variations in stellar population ages across the disk. Spectral energy distribution fitting suggests that stars in the central region are slightly older, around 120–150 million years, while stars in the outer disk are younger, roughly 50–80 million years. The observed age gradient is consistent with inside-out growth, a pattern observed in some local spiral galaxies. The dark matter halo is another key factor in the galaxy's architecture. Dynamical modeling based on rotation curves suggests a halo mass of to 10 to the power of 11 solar masses, sufficient to stabilize the disk and prevent fragmentation despite the high gas fraction of to 60%. Early universe simulations typically predict that halos of this mass would be dynamically active, subject to frequent mergers and tidal distortions. The alignment of the disk with the halo suggests that mergers were limited, or that angular momentum transfer from the halo supported disk formation. Even the distribution of gas and dust along the disk hints at early internal feedback processes shaping the architecture. Star-forming clumps in the outer disk drive localized outflows at velocities of to 100 kilometers per second, yet the central disk remains coherent. This indicates that feedback, while vigorous, was not sufficient to disrupt the disk, highlighting a delicate balance between star formation, gas dynamics, and structural stability that must have been achieved almost immediately after formation. SMACS 0723 exhibits weak tidal tails, extending roughly 200 parsecs from the outer disk. These features may represent past minor interactions or anisotropic inflows. Cosmic solitude, how isolation shapes early galaxies. While the discovery of SMACS 0723's organized disk and nascent bulge shocked astronomers, it raised an equally perplexing question. What kind of environment allowed such a galaxy to form and maintain its remarkable structure in the first 400 million years of cosmic history? Most early universe galaxies exist in dense, dynamically active regions where gravitational interactions, mergers, and gas accretion from filaments dominate evolution. However, JWST observations hint that SMACS 0723 may have formed under a far different scenario, an unexpected isolation that could have profoundly shaped its development. Wide field imaging using JWST's NIRCam and MIRI instruments reveals that within a radius of roughly 50 kiloparsecs, there are no companion galaxies with comparable stellar masses. Spectroscopic follow-up with NIRSpec failed to identify emission lines consistent with galaxies at Z is approximately equal to 10.3 nearby, implying that SMACS 0723 is not part of a dense protocluster. At this distance and redshift, typical simulations predict several neighbours with stellar masses exceeding 10 to the power of 8 solar masses, but none are observed in this region. JWST's deep field surveys show that most galaxies at Z is greater than 10 are embedded within protofilaments of the cosmic web, forming dense clusters by Z to 2-3. SMACS 0723 has an angular separation from other early structures greater than 0.5 arc-minutes, roughly 170 kiloparsecs in physical space, larger than typical for a galaxy of its mass. Simulations indicate that low-density regions can allow rotationally coherent disk formation in early epochs. Typical early galaxies acquire mass through mergers and filamentary inflows, with accretion rates at Z to 10 often exceeding 20 solar masses per year. SMACS 0723 is in a relatively low-density environment. Models suggest that cold gas streams with velocities of to 150 kilometers per second could have fed the disk directly, consistent with the alignment of stars and gas observed in near-spec kinematic maps. Moreover, environmental isolation may explain the unusually high metallicity of SMACS 0723, estimated at S 0.3 Z, based on oxygen to hydrogen ratios derived from O3 and H-beta emission lines. Most high redshift galaxies of similar mass show metallicities closer to 0.05, 0.1 Z, reflecting their nascent chemical enrichment. In dense environments, rapid mergers dilute metals and produce heterogeneous distributions, whereas in SMACS 0723, the isolation likely allowed metals produced by early supernovae to remain concentrated, leading to the observed enrichment. This is consistent with theoretical models, where isolated halos can retain enriched gas due to lower interaction-induced stripping, allowing rapid self-enrichment of the interstellar medium. JWST's infrared spectroscopy revealed variations in the galaxy's gas kinematics. The disk exhibits ordered rotation with velocities up to 5 to 75 kilometers per second, while the outer regions show faint inflows along the minor axis. These inflows are likely residual filaments from the cosmic web. Their velocity dispersion of 20 kilometers per second indicates low velocity accretion, consistent with a low-density environment. The galaxy's isolation is also reflected in the distribution of its star-forming clumps. JWST imaging shows roughly 5 to 6 luminous clumps evenly distributed across the disk, each producing 10-15 solar masses of stars per year, but none showing evidence of tidal elongation or disruption. In interacting systems at similar redshifts, clumps are often elongated or asymmetrically distributed due to gravitational perturbations from neighbours. Mergers can provide gas inflows and shocks that trigger star formation and morphological evolution, while frequent interactions can destabilize disks. SMACS 0723 has an organized disk, a central bulge, and faint spiral-like features within to 400 million years after the Big Bang. Simulations from the illustrious TNG and Blue Tides projects suggest that isolated halos of mass to 10 to the power of 11 solar masses at Z is greater than 10. Rarely develop stable disks this early, because angular momentum is typically redistributed during minor mergers. Disk formation can proceed in low-density environments with smooth, cold gas inflows, according to models. The apparent isolation of SMACS 0723 also raises questions about the distribution of dark matter. A relatively smooth dark matter halo may have supported rotationally coherent gas flows, but it also implies fewer interactions with subhalos, which would otherwise perturb the disk. JWST data suggests that the halo's density profile is consistent with a Navarro-Frenk-White profile, with a concentration parameter of C is approximately equal to 4.2, lower than typical high redshift halos of similar mass. Moreover, environmental isolation could have implications for early feedback processes. In dense clusters, supernova-driven winds and radiation pressure from neighboring galaxies can strip gas and limit star formation. SMACS 0723 has high star formation rates of to 50-60 solar masses per year across the disk. Its interstellar medium contains gas and dust, supporting ongoing star formation. Interestingly, the lack of nearby companions does not mean that SMACS 0723 evolved entirely independently. JWST imaging detected faint filaments of hydrogen and carbon emission, extending roughly 10-15 kiloparsecs from the disk plane. These filaments likely trace the remnants of cosmic web streams that delivered gas while avoiding major mergers. Their orientation along the disk's rotational axis suggests a preferential alignment, providing a natural explanation for how the galaxy maintained angular momentum and avoided the chaotic outcomes predicted by earlier models of high redshift evolution. Some galaxies discovered by JWST, including those in the CE AIRS and GLASS surveys, also appear to reside in low-density environments. Early disk formation may occur in such environments, producing organized galaxies in the first few 100 million years. This suggests diversity in early cosmic environments relevant to galaxy formation studies. Simulating the impossible. SMACS 0723. After uncovering SMACS 0723's remarkable isolation and early disk-like structure, astrophysicists faced a monumental challenge. How could existing models replicate such an advanced galaxy less than 400 million years after the Big Bang? Current cosmological simulations, from Illustris TNG to Blue Tides and Eagle, provide detailed predictions of galaxy formation, tracking billions of particles representing dark matter, gas, and stars across cosmic time. Yet none fully anticipated a galaxy of this mass. Metallicity and structural coherence at redshift Z is approximately equal to 10.3. The discovery pushed theorists into uncharted territory, forcing a re-evaluation of the parameters and physical processes underpinning early galaxy evolution. One of the first challenges arose with mass assembly. Observations suggest SMACS 0723 contains a stellar mass of roughly 3 times 10 to the power of 10 solar masses, a value significantly higher than most simulated galaxies at this epoch, which typically reach 10 to the power of 9 solar masses at Z is approximately equal to 10. Early simulations assumed a gradual build-up through minor mergers and filamentary gas accretion, but SMACS 0723's rapid growth required either exceptionally efficient star formation or an unusually massive dark matter halo. Using N-body simulations combined with hydrodynamic modeling, researchers explored scenarios involving halos exceeding 10 to the power of 11, 10 to the power of 12 solar masses, rare peaks in the density field at this early epoch. These models hint that the galaxy may reside in one of the densest early halos, despite its apparent isolation, a paradox that complicates interpretations of its environment. Gas accretion rates also posed a critical problem. Standard simulations at Z is greater than 10 predict cold gas inflows of to 10-20 solar masses per year for halos of 10 to the power of 11 solar masses. SMACS 0723, by contrast, exhibits inferred star formation rates of to 50-60 solar masses per year, implying that either the galaxy was converting gas into stars at near maximal efficiency, or that it accessed a previously unmodelled reservoir of cold gas. Recent models incorporate anisotropic filamentary accretion, in which gas streams aligned along the minor axis funnel material directly into the disk while avoiding disruptive interactions. By simulating inflows with velocities of to 120-150 km per second and low turbulence, researchers could reproduce disk-like kinematics consistent with JWST observations. Metal enrichment presented an equally thorny modelling challenge. SMACS 0723's estimated metallicity of to 0.3 Z is unusually high. Most early universe models predict metallicities closer to 0.05, 0.1 Z, reflecting the limited time for successive generations of supernovae to produce heavier elements. To reconcile this, some simulations tested top-heavy initial mass functions, or IMFs, favouring the formation of massive stars over smaller ones. Massive stars live fast and die young, exploding as supernovae within a few million years and rapidly enriching the interstellar medium. By modelling a population skewed towards stars exceeding 30-50 solar masses, researchers could generate chemical abundances matching the observed OH ratios in SMACS 0723, but such IMFs remain speculative and challenge conventional star formation theory. Angular momentum retention posed another formidable problem. Simulated high redshift galaxies often exhibit chaotic velocity fields, with mergers and turbulent inflows redistributing angular momentum and producing irregular morphologies. SMACS 0723, however, shows a remarkably coherent rotation curve, with velocities up to 75 km per second across the disk plane. To replicate this, theorists implemented simulations with low merger rates, is less than 0.1 per 100 mir, and smooth laminar gas inflows along pre-aligned filaments. By adjusting halo spin parameters to lambda is approximately equal to 0.05, slightly higher than the median for Z is greater than 10 halos. The models could preserve rotational coherence while still allowing significant star formation, offering a plausible explanation for the galaxy's ordered disk despite its youth. Another intriguing modelling avenue involves feedback processes. Supernovae and stellar winds typically expel gas from early galaxies, suppressing star formation and flattening disks. Yet SMACS 0723 appears to have maintained a dense, gas-rich disk despite vigorous star formation. Simulations explored scenarios in which feedback is directionally anisotropic, with winds preferentially escaping along polar axes rather than disrupting the disk plane. By coupling hydrodynamics with radiative transfer, models could produce gas retention efficiencies of to 70-80%, sufficient to sustain rapid star formation over tens of millions of years without destabilizing the disk. Dark matter halo structure also played a critical role. Standard Navarro-Frenk white halos with high concentrations tend to induce central starbursts that destabilize disks. To accommodate SMACS 0723, simulations tested lower concentration parameters of C is approximately equal to 4-5, allowing gas to settle gradually into a rotationally supported configuration. Intriguingly, some models required triaxial halo shapes, with the minor axis aligned with the filamentary inflow to maintain angular momentum while sustaining accretion. This fine-tuning suggests that galaxies like SMACS 0723 may form only in rare, precisely configured halos, potentially explaining their scarcity. Cosmological simulations also struggled to reproduce the observed stellar population mix. JWST data reveal both young, massive stars and more evolved populations with ages up to 200-250 Mir, implying star formation began within 100-150 Mir of the Big Bang. To model this, theorists combined early bursts of star formation with continuous, regulated inflows, producing a staggered sequence of stellar populations. This two-phase model required unusually high star formation efficiencies of to 30-40% per free-fall time, compared with the more typical 110% in lower redshift galaxies. While extreme, these parameters successfully reproduced both the integrated stellar mass and spectral energy distribution observed by JWST. Advanced simulations still struggle to capture SMACS 0723's full complexity. Incorporating magnetohydrodynamics, cosmic rays, and radiative pressure often results in over-dispersed disks or excessive starburst episodes. Hybrid models combining semi-analytic prescriptions with high-resolution hydrodynamic simulations have been tested. By adjusting parameters such as halo mass, filament geometry, feedback, anisotropy, and IMF shape, these models reproduce disk rotation, stellar mass, metallicity, and star formation rate. Although such configurations are rare, the modeling challenge extends to population statistics. Current LLCDM-based models predict fewer than one massive isolated disk galaxy per 100 megapixel cubed at Z is greater than 10. JWST deep field surveys are beginning to uncover multiple candidates with similar structures. This indicates that early disk formation could occur under a wider range of conditions than previously simulated, necessitating adjustments to assumptions about dark matter clustering, halo growth, and cold gas accretion efficiency. Additionally, SMACS 0723's properties inform the epoch of reionization timeline. High stellar mass and rapid star formation result in significant ionizing photon production. Modeling these effects involves coupling galaxy formation simulations with radiative transfer calculations to track the escape fraction of Lyman continuum photons. Estimates indicate SMACS 0723 could produce to 10 to the power of 53 ionizing photons per second, potentially affecting ionization over several hundred kiloparsecs within tens of millions of years. Modeling SMACS 0723 involves exploring non-standard cosmologies, variations in dark matter particle properties, and alternative feedback mechanisms. Even within conventional LLCDM frameworks, reproducing SMACS 0723 requires extreme parameter choices, rare halos, unusually high star formation efficiency, top-heavy IMFs, and aligned filamentary accretion, cosmic evolution under revision. The discovery of SMACS 0723 is not simply an isolated curiosity. It forces a profound rethinking of the very framework underpinning cosmic evolution. Traditional models depict the early universe as a slow, methodical tapestry of structure formation. Dark matter halos coalescing gradually, gas cooling and fragmenting into stars over hundreds of millions of years, and the first galaxies remaining small and chaotic until Z is approximately equal to 6. Yet SMACS 0723 challenges that chronology. If such massive, organized galaxies existed so early, then either our timelines for structure formation are off, or some physics in the early universe is yet unaccounted for. One immediate implication concerns star formation efficiency in the first few 100 million years. In standard models, high redshift galaxies convert only about 1/5% of their gas into stars per dynamical time, constrained by feedback from supernovae and radiation pressure. SMACS 0723, however, exhibits star formation rates of 50-60 solar masses per year, suggesting an efficiency of to 30-40% per freefall time. Early gas may have been exceptionally cold and dense, facilitating rapid fragmentation, or early feedback mechanisms may have been less disruptive than previously assumed. Chemical evolution models also require revision. Supernova enrichment may have occurred rapidly, possibly via an early population of population 3 stars. Massive, short-lived stars hypothesized to form within 100-200 mir of the Big Bang. The presence of metals so early indicates that the interstellar medium was chemically enriched faster than models based on pair instability supernova rates predict. Observations of early galaxies suggest this rapid enrichment may have influenced cooling and star formation. SMACS 0723 provides data relevant to dark matter halo assembly. Standard LCDM cosmology predicts that halos massive enough to host galaxies of this size at Z is approximately equal to 10 are rare, about 1 per 100 mpc cubed. JWST observations reveal several candidates with comparable mass and structure. Filamentary inflows, predicted by simulations such as blue tides and illustrious TNG, may have supplied the gas and angular momentum needed to form these early massive disks. Another striking consequence concerns the timeline of cosmic reionization. Prior to Z is approximately equal to 10. The intergalactic medium is mostly neutral, with ionizing photons slowly carving out bubbles around early galaxies. SMACS 0723, with its star formation rate, could produce to 10 to the power of 53 ionizing photons per second, influencing its local environment over hundreds of kiloparsecs. Observations suggest that the contribution of such galaxies may need to be included in cosmological models, requiring recalculating ionization histories to account for early ultraviolet radiation. The galaxy's angular momentum and disk-like morphology also upend expectations for early cosmic dynamics. Most simulations anticipate that frequent mergers and turbulent inflows dominate at Z is greater than 8, producing irregular, clumpy galaxies. SMACS 0723's rotational velocities of to 75 km per second and coherent disk structure indicate that some halos preserved angular momentum over tens of millions of years despite dense environments. Disk formation in these cases can occur concurrently with rapid mass assembly when conditions such as low merger rates, triaxial halo shapes, and aligned gas inflows are present. Beyond individual galaxy evolution, SMACS 0723 indicates that the population statistics of early massive galaxies may be higher than current models predict. Semi-analytic models, or SAMs, suggested fewer than 0.01 galaxies per mpc cubed, with stellar masses above 10 to the power of 10 solar masses at Z is approximately equal to 10. But JWST observations show that the actual number could be roughly 10 times higher. This requires adjustments to halo occupation distributions and stellar mass functions used in simulations of cosmic structure formation. The discovery also impacts our understanding of stellar population evolution. Spectroscopic analyses reveal both young, massive stars and older populations up to 200-250 mir, indicating that star formation began shortly after the first dark matter halos collapsed. Standard models set the delay time between halo formation and sustained star formation at to 100-200 mir, but observations of SMACS 0723 indicate that this delay could be much shorter. SMACS 0723's rapid evolution raises questions about feedback and quenching mechanisms at high redshift. In lower redshift galaxies, stellar winds, supernova explosions, and active galactic nuclei regulate star formation, preventing runaway growth. SMACS 0723, however, achieved high stellar mass without obvious quenching. Feedback at Z is greater than 10 may operate differently, possibly being less isotropic or more easily vented through polar outflows, allowing disks to retain gas while sustaining star formation. Furthermore, the existence of galaxies like SMACS 0723 could affect interpretations of cosmic infrared background measurements. SMACS 0723 and similar high redshift disks emit substantial near and mid-infrared light, contributing to the cumulative background detected by Spitzer, Herschel, and JWST. Modeling these contributions allows estimates of stellar and dust production at Z is greater than 10. The implications extend to dark matter physics. The rapid assembly of massive, rotationally supported galaxies challenges assumptions about halo growth in LCDM cosmology. Some models suggest that warm dark matter, WDM, with particle masses of 213 keV, could suppress small-scale structure and support the early formation of massive halos. Standard cold dark matter models remain viable, but alternative scenarios are being tested to match observations of early massive disks. Finally, SMACS 0723 highlights the capabilities of JWST. By revealing galaxies that do not fit conventional timelines, JWST provides detailed data on early cosmic history. Observations of these early massive galaxies lead researchers to update models of star formation efficiency, halo growth, chemical enrichment, angular momentum retention, and feedback mechanisms. Each observation contributes to refining simulations of galaxy formation and the evolution of the universe during the first 500 million years. What JWST could reveal next? If the discovery of SMACS 0723 has rewritten the early chapters of cosmic history, the question now is, what lies beyond? JWST's unprecedented capabilities promise to peel back layers of the universe never before glimpsed, not just revealing isolated anomalies, but reshaping our understanding of galaxy formation, stellar evolution, and even the nature of dark matter. The telescope's combination of sensitivity, resolution, and infrared reach creates a window into epochs previously invisible, and every new observation carries the potential to overturn long-held assumptions. One of JWST's immediate goals is to identify additional impossible galaxies. SMACS 0723, with its stellar mass of to 3 × 10⁻10 m at Z, is approximately equal to 10.3. Already challenged LCDM predictions. Early JWST surveys, including Cosmos Web, CEERS, or Cosmic Evolution Early Release Science Survey, and PRIMA, or Prime Extragalactic Areas for Reionization and Lensing Science, have identified candidates with comparable masses at Z equals 911. These galaxies appear both massive and structured, suggesting that what once seemed a rare anomaly may represent a significant, previously hidden population. JWST's deep field imaging, achieving magnitudes of M/AB, is approximately equal to 31 inches. NIRCam allows astronomers to detect sources as faint as 1020 NJY, effectively probing galaxies with stellar masses down to MB 10⁸ m at redshifts beyond 12. Beyond sheer numbers, JWST's spectroscopic instruments, particularly NIRSpec and MIRI, are poised to reveal the chemical fingerprints of early galaxies. Previous surveys, limited by Hubble's wavelength coverage, could only infer metallicities indirectly. JWST can detect emission lines such as OIIE 5070, H alpha, and H beta in galaxies at Z is greater than 9, allowing direct measurements of metallicity, ionization states, and gas temperatures. Early results indicate that some galaxies already possess 0.2–0.5 Z, suggesting rapid chemical enrichment. Future observations will determine whether SMACS 0723 was an outlier or part of a broader trend of early heavy element production, challenging standard models of population 3 star formation and supernova rates. JWST also promises to illuminate the first billion years of reionization with unprecedented clarity. By detecting galaxies beyond Z is approximately equal to 12, and measuring Lyman alpha emission or its absence, astronomers can map the evolving ionization state of the intergalactic medium. Recent models predict that at Z is approximately equal to 1213, the neutral fraction of hydrogen was approximately 70–80%. But JWST's ability to detect faint ionizing sources could reveal pockets of early reionization driven by surprisingly luminous galaxies. Observing the spatial distribution of these ionizing galaxies will help determine whether reionization proceeded inside out, from dense regions outward, or more patchily than anticipated. The telescope's infrared reach is particularly crucial for studying dust and molecular gas in the early universe. ALMA has already detected CO and CII. Emission in some Z is approximately equal to 7 galaxies, implying dust masses to 10 to the power of 6, 10 to the power of 7 m. But JWST can extend these observations to Z is greater than 10 with NIRCam and MIRI imaging and spectroscopy. Understanding how dust forms so early, whether through rapid supernova condensation or evolved stellar winds, is critical, as dust affects both star formation and the escape fraction of ionizing photons. Early observations of candidate galaxies show dust-to-gas ratios of to 1%, suggesting that dust production may have accelerated faster than models predict. JWST will characterize galaxy morphology in the first few 100 million years. SMACS 0723's disk-like structure at Z is approximately equal to 10 was observed, and upcoming programs aim to statistically study galaxy shapes at Z equals 8 at 12. NIRCam imaging with to 0.03 arcsecond resolution allows astronomers to discern clumpy, irregular, or coherent structures on scales of 2, 200, and 300 parsecs at these redshifts. Preliminary surveys indicate that while most galaxies remain irregular, a fraction exhibit early signs of rotational support. Another frontier JWST will explore is the prevalence of massive black holes in the early universe. SMACS 0723 shows no evidence of AGN activity, yet the rapid assembly of massive galaxies implies a potential for equally rapid black hole growth. X-ray stacking surveys and NIRS spectroscopy of high ionization lines such as NV10240 or CIV 15490 will probe accreting black holes in Z is greater than 10 galaxies. Current theoretical models suggest black holes of 10 to the power of 5, 10 to the power of 6 m could form within 200–300 mir if seed black holes accrete efficiently, and JWST may finally provide observational confirmation or constraints on these predictions. JWST's surveys will constrain the abundance of high redshift galaxies. Standard LECDM simulations predict only a few galaxies above 10 to the power of 10 m at Z is greater than 10 per 100 megapixel cubed, yet early JWST observations hint at higher number densities. Programs such as JWST Advanced Deep Extragalactic Survey and GRISM Lens Amplified Survey from space will refine luminosity functions at Z is greater than 9 and provide data relevant to dark matter halo assembly, star formation efficiency, and the expansion history of the universe. JWST is positioned to detect population 3 star clusters, the first generation of stars composed almost entirely of hydrogen and helium. While none have been confirmed, simulations suggest that clusters of 10 to the power of 4, 10 to the power of 5 m could be luminous in the infrared due to massive, short-lived stars emitting primarily in UV, redshifted into NIRCam's 1.5 micrometers range. Observing such clusters would provide information about primordial nucleosynthesis, the initial mass function of the first stars, and the timeline of metal enrichment. Beyond individual galaxies, JWST will probe the cosmic web at unprecedented resolution. Gravitational lensing by galaxy clusters like Abell 2744 magnifies faint background sources, allowing NIRCam and MIRI to map early filamentary structures connecting galaxies. These observations will clarify how gas flows along filaments feed early galaxies, potentially explaining the rapid assembly of massive disks like SMACS 0723. Understanding the connectivity of the cosmic web at Z is greater than 10 also informs models of early galaxy clustering and the influence of the environment on star formation rates. Another exciting avenue involves time-domain cosmology. JWST's repeated observations of deep fields may detect supernovae from the first generations of stars, including potential pair instability supernovae from population 3 progenitors. These explosions, with luminosities up to 10 to the power of 44 epochs, could be observable. Out to Z is approximately equal to 15, providing direct evidence of early stellar populations and metal enrichment processes. Detecting such events would constrain supernova feedback, chemical evolution, and the initial mass function at extreme redshifts. JWST is also poised to refine our understanding of galactic rotation and dynamics in the early universe. Using spatially resolved spectroscopy with NIRSpec, astronomers can map velocity fields of high redshift galaxies with precision of to 10 kilometers per second. This allows measurement of rotation curves, velocity dispersions, and dynamical mass, providing crucial tests of early galaxy formation models and dark matter halo predictions. By comparing kinematics across dozens of Z is greater than 9 galaxies, JWST will help determine whether rotational support was common or exceptional in the universe's first few 100 million years. JWST's discoveries will guide future missions. Observations of early massive galaxies, chemically enriched systems, and potential population 3 clusters will inform the design of next-generation telescopes, such as Louvois, Origin Space Telescope, and the Roman Space Telescope, defining survey strategies, wavelength priorities, and sensitivity requirements. Each detection provides data to constrain early universe physics. JWST will expand the sample size of high redshift galaxies from single digits to hundreds through campaigns like CEERS, JADES, PRIMA, and GLASS. This allows measurement of metallicities, star formation rates, dynamics, and ionizing output for galaxies at epochs previously inaccessible. Observations include massive, disk-like galaxies at Z is greater than 10, chemically enriched star clusters, and early black holes. JWST will uncover hundreds of galaxies more massive than 10 to the power of 10, M at Z is greater than 10, detect supernovae from early stars, map filamentary structures of the cosmic web, and measure chemical abundances. These observations will provide data to refine models of galaxy formation, star formation efficiency, and cosmic evolution. JWST captures photons emitted when the universe was less than 400 million years old. JWST has already provided observations showing complexity and dynamism in the early universe beyond previous models. Upcoming discoveries are expected to expand the dataset of high redshift galaxies and related phenomena, further informing models of cosmic structure and evolution.